We'll have two groups from Africa, one from Zambia, one from Zimbabwe, connected midnight tonight. And I've sent them the new link also. Are you on the 8:02 target? The one you were going to start at 8:02?
Yes.
No. Oh,
Yeah,
oh,
we are.
no.
Yeah, we're just about finished on this last exposure here, and then we will move to another similarly bright Andromeda transient.
Got it. Transient
Or
or
variable.
Variable.
Sorry.
Okay, variable. You got my attention. Okay, I'm looking at the. So the Stephanie, you're using one VNC, Monica, you're using one, and Kevin's using one, or has only one in use right now?
I think it's just me and Kevin right now.
That's fine. That's fine. Yeah, because you don't. I don't need to be on a VNC. So for those who are
the strangest looking cosmic rays I've ever seen.
string theory.
Yeah, confirmed.
Yes, indeed, indeed. All right, that so I'm recording the call, and for those of you who heard the bell, you should have heard a bell. That was the end of the exposure. You can see it says remaining 0, elapsed 200 in that window, and here too it says here this one is about to finish. It's counting down the last 5 seconds. So it takes red side and blue. There are two. It's really two spectrographs in one. It's a double spectrograph. The long wavelength light goes into a red spectrograph. The short wavelength light goes into a blue spectrograph, and we really collect. We first split the light down the middle, and then spread out each half into the constituent colors of the rainbow, and that's what's going on here. And that little star with the crosshairs on
Sorry,
it.
Raja.
Yeah.
I have sent new coordinates to POCO, and we are ready to move.
Okay, I'll move.
And I have a PA of 105.
105, got it.
I will narrow the slit. Should be also 16th-ish magnitude, also relatively isolated. Oh, sorry, like 15.3, even brighter.
And are you taking a couple of 2-minute exposures?
Usually like 300. Sorry, 3 200-second exposures.
3 200s, I see. So a total of 10 minutes.
Mm-hmm.
Got it. I'm trying to gauge how much time I have to yap.
10 minutes is
Yeah, 10 minutes
is pretty good.
Yeah.
I can finish my sandwich in that time.
Let's see, who just joined? Was that Raphael? While this is recording, I am going to quickly go to the other call on my phone and see what I can do to make sure no one's waiting there.
Okay, we've got a little bit of wind shake here. Is that how narrow the slit is going to be?
No, it's going to open up.
Okay, why don't you go ahead and take the slit back? I want to make sure that we are able to keep this centered, given the wind shake we've got.
Sean, are you on a Polycom or a regular laptop?
I'm on a regular system.
Okay. Oh, so you had no trouble switching over to this Zoom call then?
There was a little trouble, but we got it worked out.
Okay, thank you.
Yeah. We're having
Appreciate it.
audio issues.
Okay, thank you for working that out. I really appreciate it.
Okay, we are centered. I'm going to mirror position 3 to find something to guide on. And you may begin.
Okay, Russia, you have 10 minutes.
I have 10 minutes.
Plus readout.
Plus readout. I see a lot of familiar faces on the call. I see Casey and Kiara, who are UCSC undergraduates who are working with me on different projects. Welcome. Casey, I haven't spoken to you in a little bit. Welcome. Kiara, same to you. Welcome. And I'll quickly introduce our observing team, starting with Sean. Sean Stone is our observing assistant. He's in charge of making sure the telescope and observatory and instrument stay, are running properly and safe from weather elements and all that. Sean, would you like to say anything else about your role here?
Well, you pretty much summarized it. I'm mostly here to protect the telescope and to make sure that we get on the appropriate target and stay on it so that you can get your observations.
And Sean, your connection says 120 ROR. So 120 must be the 120-inch telescope, and ROR is that readout room?
That is correct.
Okay. Okay. So this is where the, where when we would go to the mountaintop to use the telescope, we would be sitting at desks that are right next to where Sean is sitting. We wouldn't be sitting in the cold space of the dome, but we would be sitting in a room that's heated. And I'm emphasizing this separation because we want to keep the telescope at sort of outside ambient temperature so that we don't create turbulence, convection from hot and cold air mixing in the same room. So we would sit in the warm room that Sean is in and operate the telescope from there. Right next to that, 2 doors away from that, is where the main dome of the telescope is. This particular telescope, Lake Observatory, is in California, east of the city of San Jose, on a mountain that's now called Mount Hamilton. It is a telescope we are really fortunate to use. It's a telescope that's been around for quite a bit of time, almost 50 years. Almost. I think this telescope was put together in the 70s, if I remember correctly, the 120-inch, and here we are in 2021. The spectrograph we're using is called the CAST spectrograph. We're taking spectra of individual stars at once, one at a time. Okay, Kevin and Monica and Stephanie, if you wanted to introduce yourself, that would be terrific, please. We're recording this. Kevin, take it away, please.
You caught me with a mouthful of food.
Okay, Stephanie, you're the lead on this run, so please say a little bit about yourself.
Sorry, I was muted. So I'm a 4th year at UCSC, and I've been working on this project for 2 years. And yeah, so basically I just make a list of stars to observe tonight, and I keep track of them. And yeah, I just like make sure everything's going smoothly with the stars and everything. And I also reduce them and reduce the data in real time so that we can see what's going on with them.
And real time is particularly important because the kind of stars that Stephanie is taking, mentioned in that list, these are all stars that are special in the following way. Most stars, they stay the same brightness from hour to hour, night to night, week to week, year to year, decade to decade, right? I mean, the sun has been this way for millions of years, the same, effectively the same brightness, very minor changes for millions of years. These stars undergo drastic change on timescales of, certainly on timescales of months, but sometimes even on timescales of hours or days. So these are called variable stars. So what is variable is their brightness. Their brightness varies with time. And that's one class of objects. Another class of objects are those that were not even visible before. They pop into existence. They become so much brighter than they were before that they weren't visible before. They suddenly become visible, and then they fade out of visibility again. Those are called transients, where they appear transiently and then disappear, whereas variable stars are always visible, but they change in brightness. You can think of them as one is a more extreme version of the other. When the change in brightness is drastic enough, it can go from being invisible to being visible and then back to being invisible. So our project is called Salvation, which is spectroscopic analysis of luminous variables and transients in our neighbor. Our neighbor is the Andromeda Galaxy. So these stars we're looking at, this very star that we are taking a spectrum of right now, is 2.5 million light years away. Kevin, how are you with your mouthful of food?
I have swallowed. 1 sec, I'm just getting our next target on the list. I'm having some slow internet issues. There we go. Yeah, hi everyone. I guess I'm now a 5th year PhD student at UCSC. So I've been here a while. I've been involved in this project for, I think, 3 years now. And I've been working predominantly with Raja at the university, and then another faculty, Connie Ricosi, are my 2 main advisors, and then a group of other collaborators as well, including Monica here. Predominantly what I think about in my work is on using spectra of stars, so very similar to this project, but generally what I think about is stars in our own galaxy, and particularly stars that are pretty old and faint and into the farthest out regions of our galaxy. And so by measuring their spectra, we can try to measure properties like their surface temperatures and their surface gravities. We can use that to try to learn about their distances. And then in particular, we can try to learn about their chemical properties by the kind of the chemical fingerprints that end up in a star's spectrum as the light passes through the outer regions of its atmosphere on its way to us. And so what I'm usually interested in is measuring the chemical properties of stars from their spectra so that we can have an understanding of how our galaxy formed and evolved. And the technique of measuring properties from stars is pretty applicable to lots of projects, including this one.
Thanks, Kevin. Monica, your turn.
You're muted, Monica.
Can you hear me now?
Yeah, we can hear you.
Okay. Hi, everyone. My name is Monica Saraison. I just started at Gemini North in Hilo as an associate scientist. So I've been working with Raja, Kevin, Stephanie, and Rafael on this project since, I think, 2019.
March 2018.
Oh, sorry. No, I think that was for pulsations.
You're right. You're right. The
for
spectroscopy.
salvation. Exactly.
You're right. Absolutely right. Fall 2019.
Right. Yeah. So for this project, I help out with the target selection, coordinating the observing run with his fabulous students, and sort of just planning the science publication that can come out of it. Generally, for my own research, I do time domain astronomy, so just as like Raja described. I study variable stars and transients in the nearby galaxies. I work with data a lot, both with on the archival data that's like from past surveys, as well as data that we get from ongoing surveys in real time to find interesting, unique astrophysical events that we can use, for example, LickStS and all these big telescopes to follow up to understand the nature of those events. So yeah, welcome and enjoy this run.
So Monica and Kevin and Stephanie are being super modest. I mean, Monica is one of the world's experts on variable stars and transients. Kevin is one of the world's experts on spectroscopy of stars to measure chemical abundances. So, and Stephanie, Raphael, well, in fact, Kiara, Casey, they're on their way to becoming experts in their fields of research. So it's, I just want to say that the modern day world leaders in science, not just astronomy, don't wear white lab coats, and they may not fit your image of a scientist. And I think that's a really important part of this of these Zoom calls, is to see who today's scientists are. And they're located all over the world. They're not all in one place. Our science team today, Monica's sitting in Hilo. Stephanie's in are you in Southern California, Stephanie, today, or where are you? Are you in Santa Cruz?
Sorry, Raj, I don't want to cut you off, but
No, you should go ahead.
We're about to read out and move to a
No, please go ahead, Kevin, please.
Then you'll have 15 minutes. Okay, we are reading out on red. I am sending new coordinates to POCO, and we are ready to move.
On the move.
This one's a bit fainter than the others, but still isolated, so hopefully not confusing.
Okay, let me know when you have that PA.
I have a PA of 103.
103, got it.
So the thing we're looking at right now is kind of like a webcam pointed at the sky, or effectively pointed at the sky. And so you'll see these stars come into the screen, come into and out of focus. Sometimes you'll see squiggly lines as the telescope is taking an exposure and moving. But right now we're near where we want to be. And so Sean is trying to identify our target and then get it located in the slit of the telescope, which is this. Maybe you can see a faint line here.
Do you have to narrow the slit, Kevin?
I thought I did. Oh, I did not.
Thank you.
It's a little bit easier to see here. So there's a slit here, and then there's something near the center of the slit that's a bit brighter. That's our target.
Right there in the red box is your target.
Yeah. There we go.
And the reason that line looks dark, the horizontal line looks dark, is it's a cut in a piece of reflective metal. So where the metal is reflective, we can see the light. Where there's a cut, the light is going through that cut into the spectrograph, where it can be spread out by something like a prism and a grating.
You may take a step back.
Okay.
Sorry to interrupt.
No, not at all. Not at all. Please. I'm interrupting the observations, not the other way around. I'm a little worried that Raphael hasn't connected yet, so I'm going to go get my phone and connect on my phone to the other call and see if Raphael's there or others are there.
Sorry, Sean, did I miss you saying if we're good to go?
You're good to go, yes.
Okay. course, I forgot to write down the name of the last target. That's okay.
Are you using the, what is it called? Isn't there a option to send the coordinates to?
Yes.
What is
But that doesn't help me figure out the last one. That's okay.
fine. No, I see.
It's okay. I have a list elsewhere.
Is this one of Shukunna's stars whose spectrum I'm seeing here on the in the blue window?
Yes, I was pulling this up because it's such a bright target that we can talk about some of the
Yeah, Balmer series. It's
the
so
Balmer
pretty.
series and you know the things that you can learn from a star's spectrum by looking at these different features.
And is that H beta the reddest line?
Yes.
In this, okay.
Yeah.
H beta, H gamma.
Yeah.
Delta. Epsilon.
So basically what I've done here is in one of these exposures for a different star, not the one we're looking at here or the one we're looking at now, we took a spectrum and it produces something just like this. And then I basically, I take a line along the horizontal direction here. And that gives me the plot that I'm seeing here, which is kind of like a spectrum where we're asking about the amount of light at each one of these pixels. And you can think about that as basically saying the light as a function of wavelength. So this is almost like a spectrum. It's not calibrated or anything, but it gives you a good sense of some of the features you can see in a star. Some of the shape that you're seeing here is just because of how the detector responds to light. It is not very sensitive on this edge or the other edge, either end. But in general, the thing that I want to focus on is the fact that you see these deep lines here. There seems to be a generally continuous shape, but then every now and then you see these big dips. And these big dips that you see by eye are all from hydrogen, the atmosphere of the star. As the photons from the center of the star are coming out, they're going to interact with the hydrogen in the atmosphere, and in particular, they're going to interact by sending electrons up into higher orbital energies, and then that cascades down, and it produces the features that you're seeing here by scattering light out of our line of sight. But if I zoom in on a particular feature like this one, this here is H beta. So maybe you've heard of this from your science classes, your physics classes, your Balmer series. So this is the second in the Balmer series. And this is, we can use something like this very strong line here to learn a lot of things about the star. In particular, we can measure the location of this feature and compare it to where we think this feature should be because of where we measured it in some lab on Earth. And then that difference is because of the relative motion between the star and us. So if I think that the feature should be centered over here, but it's over here, that means that the light has been blue shifted. Versus, if I think the feature should be over here, but it occurs over here, then the light is red shifted. And so red shifted meaning the star is moving away from us, blue shifted meaning the star is moving towards us. So we can use that to measure the star's velocity with respect to us. We can also use the shape of this line to learn about the temperature and the pressure at the surface of the star. I won't go into that so much, but you can imagine if you have like a really dense environment, you're going to create a much broader line than a more diffuse environment. And then the other thing, so this is a Balmer line. This means it's associated with hydrogen. But if I pick a different feature that's maybe not as strong as one of these other ones, all of these really strong features here are from hydrogen. But there are other features here, and I'm not sure what they belong to, but you might see a little feature like this one here. And this, and I'm just gonna I'm not gonna make a guess, but I'm gonna say, this could correspond to a different chemical in the atmosphere of the star that isn't hydrogen. For example, it could be magnesium, or it could be iron in the atmosphere of the star. And in the same way that light interacts with hydrogen, it's also going to interact with the other elements in the star's atmosphere. And so the strength and the shape of this line is telling you about how much of that chemical there is. And so if you measure a feature that corresponds to a particular element, you've confirmed or denied the presence of that chemical in the star's atmosphere. And then you can also use it to quantify how much of that element there is in the star, which tells you about kind of the environment that that star was born in. So that's kind of some of the research that I do.
One of the cool things you can see in the spectrum is these really deep dips. Notice how they get closer and closer and closer as you march to the left. And for all of these dips, as Kevin said, they're produced by hydrogen. But in all cases, the hydrogen starts from level 2, energy level 2, and due to the absorption of light from the interior of the star, it's trying to escape from the interior of the star, due to absorption of that light, depending on what kind of photon it absorbs, the electron can jump from level 2 to level 3. That would produce H alpha that you don't see here. It's in the red half of the spectrum. It produces H beta when it jumps from level 2 to level 4. 2 to 5 is H gamma, 2 to 6 is H delta, and so on. You go down the letters, the Greek alphabet. But one of the cool things is the higher energy levels are actually closer and closer and closer together in energy. So when you go from 2 to 4 versus 2 to 5, that's a big difference in energy, but 5 to 6 is a smaller difference. 6 to 7 is a smaller difference. So you see how, you notice how the lines are getting closer and closer together horizontally. That is actually directly reflective of the energy levels within the hydrogen atom. Now, mind you, these energy levels in a hydrogen atom that we're measuring, these energy levels are the same within that star that we're observing here as they are in our laboratory. That's one of the beautiful things about this kind of physics. Quantum mechanics applies to atoms in stars, it applies to atoms in our laboratory. And that's really important for this, because without that, we wouldn't be able to read the light and interpret it in the way we can.
Yeah, good clarification.
Marufa, I don't know why people pray to the sun. I mean, they give us light, it gives us light, keeps us safe during the day. That light is such a big part. I mean, especially for ancient people, that light was such a big part of, our vision was such a big part of staying safe, from, predators, from animals in the wild. So I don't know. I mean, sun worship is so common across the world, in Egypt, in India, it's such a powerful presence for us in terms of heat and light. Gives us the warmth to remain alive as warm-blooded animals, and also gives us light to use our vision to stay safe. That's the best I can come up with. Kiara, thanks. Thanks so much.
Thank you. Thank you. I really appreciate answering this question. I hope it didn't sound like a dumb question. I always think about it.
There is no such thing as a dumb question here. Our Zoom calls are dumb questions free. What about, tell us about yourself, Marufa. How did you find out about this session?
Oh, Sam is my friend from University of Hawaii Manoa Circle. I was electrical engineering, my second master's at UH Manoa, and I'm born and raised in Bangladesh, and I'm now a CEO of my own company called Everest Innovation Lab.
Wow.
And also, I'm trained as an astronaut. I finished 3 trainings.
Wow.
And and I'll be speaking this week in a conference for 1 million people on Mars. It's
wow. Wow.
Yeah.
Nice
to meet you.
Very nice to meet you, Marufa. And you're in Honolulu then?
No, I'm right now on Molokai.
On Molokai, I see. I go to the Big Island a lot. I'm in California, but I go to the Big Island a lot to use the telescopes in Mauna Kea.
Second question, by the way, because I just remembered this question, very important to me. How does the telescope, like remote astronomer, what is the job of a remote astronomer? If that person is not located on the Big Island exactly, how can they do research? And
right. No, so this is a very good question. In fact, here, we're not using a telescope in Mauna Kea tonight, of course, we're using one in California, but it's really a matter of teamwork, right? Sean knows the telescope and the instrument and how to keep it safe. And Monica, Kevin, Stephanie, Raphael, and I, we are scientists, we're astronomers, we have some understanding of the capabilities of the telescope and instrument, and we know what kind of measurements we need to make to answer some science questions. What happens to stars when when their brightness varies? What happens?
So what
to
is your background? You studied astronomy or physics?
I studied physics in college, physics, math, and chemistry when I was an undergraduate.
Not
And
college, like your PhD in what?
my PhD was in astrophysical sciences. My PhD was in astrophysics. So, first 2 years we had to take classes on, stars.
Which country?
I studied in the US. My PhD was at Princeton University on the East Coast.
Oh,
But I before that, I was in college in Kolkata.
oh wow! So they speak Bengali.
I do speak Bengali. In fact, both my parents were born in what is now
Yeah.
Bangladesh. My mother's from Dhaka, my father's from Borishal.
Oh wow! Really? I'm from Bangladesh. So I
Yeah.
can speak Bengali, Hindi, Urdu, Arabic, some Hawaiian language like Tars and Nepali, Moithili, Arabic. Yeah.
Wow.
Nice to meet you.
Very
I'll
nice
just
to meet
mute myself and just listen in.
Oh,
Thank you
thank
for your question.
Thank you, Marufa.
Yeah.
Yeah.
You're welcome.
Monica, I'm going to Kevin and Stephanie. I'm going to go to look for Rafael on the other Zoom call. Okay, I'll connect by my phone.
Sounds good.
I'll leave this running and recording, but people should, yeah, you feel free to ask questions of Kevin, Monica, and Stephanie.
Monica, one of the questions in the chat is, what is the most surprising thing your research has discovered so far? I think my answer to that is, it depends on the project that you're working on. Every time, everything new is always exciting.
Yeah.
I think for this particular project, it's probably the Red Nova, right? That Stephanie's
Working on.
working on right now. If you want to talk about that.
Okay, that's good. Wait, hold on. I'm eating popcorn. Let me just swallow.
Yeah.
Okay, so the Red Nova, it's a really rare type of supernova. And we've gotten a couple of observations of it. And it's really interesting to see it progress. And like the different properties that it has. It has like a double peak. So that's something that's really interesting about it, and like makes it unique from other supernovas. And it's also in this like really like weird transient gap where not a lot of observations are. So it's really cool to like go into that gap and see what other like supernovas exist there, instead of like the ordinary like classical and like just like the ordinary ones. It's like always fun to like look at a really rare like type of star or whatever it is. So like I feel really lucky to be like observing that supernova.
So just to add to that, it's so the nature of the Red Nova is not known yet. It's still a mystery how it originates. So I think I would not call it a supernova, Stephanie. Maybe I would call it something in the gap, like whose brightness is
Like a luminous nova.
yeah. So whose brightness is maybe like a 1,000, or that's an exaggeration, but maybe a millionth of a supernova in terms of luminosity.
Yeah.
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 So but it's just as Stephanie said, it's only a handful known, 12 or so that you documented, and for us to discover this, in our campaign, even if we didn't start out looking for it, so that was sort of serendipitous. So that surprising element is also very exciting for us. So that way we gather, we use our available time to gather more information if we can on this event, and with all these spectral observations, we try to make sense of the underlying physics of that event.
But on top of that, we have in some of our transient observations, we'll find something interesting, and because it's something that is only on for a little while before it's gone forever, we'll send out an astronomer's telegram to the community, or basically an email blast that tells everyone, hey, if you're interested in this particular type of object, you should point your telescopes here. So it's always fun when we find something like that and tell the community, hey, this is something interesting that you should check out. Okay, Sean, we are reading out on red. So I'm going to send new coordinates to POCO, and we are ready to move when you're ready.
Roger that. We are on the move. Also, let you know my relief has arrived. He will be taking
Okay.
over this target.
Sounds good. Who do we have with us for the rest of the night?
Dan is going to be taking over for him.
Dan is our man. Sounds good.
And let me know when you have that PA.
Yes, I keep forgetting to give that to you. I have a PA of 101.
101. Got it. Okay, you may take the slip back.
Slip is back.
And you may begin your exposure.
There we go.
We are guiding. How long are we here for?
15 minutes. Seems like the seeing is improved a little bit.
Yeah, that was part of our conversation with my counterpart here. It looks like things have gotten better. I'm anxious
Perfect.
to find out what the estimate is going to be when we refocus and get a new estimate.
Right. To continue on with what we were saying a bit ago about kind of the goals of this project, one of the, I think if you're not, in the field and you're not reading papers regularly, it's kind of easy to think that we understand everything about what's out there. We know a lot about stars because we've been studying them for forever, but it's surprising how kind of uncertain everything is, and how how little we know about even the things that we think we know about. And what I mean by this is there are, if you go back 50 years, the number of different types of stars that we knew that pulsated in particular ways was kind of a small list of things. And in the last 50 years, that number is, I don't know, quadrupled. We know of some, I don't know, 50 different types of stars that change in different ways, as opposed to the 10 we used to know about. And the reasons why they do this, the reasons why each one of those different groups do that is not very well understood. And it's not well understood what's actually happening to the star itself. Is it puffing up? What's happening to its atmosphere? Is it what's happening when it's contracting? On what time scales do these things change? What's happening to the different, as you look at the star, are you looking at different depths into the star, and what are the different properties of those depths? And so that's kind of the goals of this project, is to look at some of those really weird, really different types of stars, maybe find some new different types of pulsating stars, and to particularly look at different examples of stars that are changing over time, and get measurements of their spectra at multiple times throughout their pulsation period, so that we can measure their properties at each point that we measure the spectrum, and then try to learn something about the underlying physics. So, this type of star pulsates like this. Its radius is changing like this. Its luminosity is changing like this. Its gravity is changing like this, to try to help us understand properties of stars in general, and to learn some new things about stellar physics. So that's kind of like the underlying goal of this project.
Kevin, sorry to interrupt. I went to the other Zoom call,
Mhm.
and Raphael is still connected to it, but he wasn't on it. And but I'm just going to step aside, have dinner, and be right back. This is still
Okay.
recording, and please continue. Sorry to interrupt.
No, that's okay.
I'll mute and step aside.
Another question from Ken: why are we studying spectra of variables in Andromeda? To learn about our own galaxy? And yeah, to a certain degree, I think Andromeda is one of these really good. So okay, when you're trying to study populations of stars, and in particular rare types of stars, you want as many stars that you can look at as possible. And as you start looking at really far away galaxies, you can't really make out individual stars. But luckily for us, we have this nearby neighbor that's a galaxy of pretty much the same size as our own, which is Andromeda. And it's close enough that we're actually able to make out individual stars. So we're able to look at the whole disk of Andromeda, and that's, millions and millions and millions of stars. And so you're more likely to see lots of different types of stars. And if there's only one star in 1,000 is doing something really weird, well, you have like tons of stars to look at, and so your chances of seeing some of these really weird stars are significantly improved. And so that's part of the reason why looking towards Andromeda is really useful. And you might wonder, like, why wouldn't we look in our own galaxy? And the reason is, we're inside of our galaxy. It's really hard to see all of. We don't see very many stars in our galaxy, just because there's dust towards the galactic center. We're not able to see through the disk of our galaxy. So we can see a lot more stars in Andromeda than we're able to see in our own galaxy. And we're not necessarily learning about our own galaxy in this way, other than by understanding stars better, understanding different types of stars, understanding how stars form and evolve. We are able to understand the stars in our own galaxy better, which helps us, understand the universe better. Can we tell if these variables are binary? Ooh, good question. So there's lots of different types of binaries. So I'm not sure exactly which type you mean. There's two stars that are nearby each other on the sky, and so it looks like they're binaries, but if you were to see them in 3D, they'd be separated by light years from each other. So that's one type of binary. There's other types of binaries where they're so close that it's hard to tell that it's two things until you go and take a spectrum, and then you can see like chemical signatures from multiple things. That's another type of binary. And are they actually orbiting each other? And that's I think that's maybe the question you're asking. And in some of these cases, the answer is I don't know that the variables. I guess some of the variables could be binaries. There's a classical type of novae called a classical novae, where okay, Monica. There's a classical novae, which is where you have a star and another star that are orbiting each other, but one of them's basically already gone through the stages of its life. It's puffed up its envelope. It's turned into a white dwarf, and so it's just the core of a star left over. It's not dense enough to become a black hole, but it is a very dense object. And next to it, its orbiting companion is another star that's still evolving, and eventually it'll reach the later stages of its life. It'll puff up its envelope, and eventually it can start feeding some of its outer envelope onto the other star. So you have two stars orbiting each other. One of them is this like dense core, and the other one's this puffy thing that's kind of funneling mass onto the other one. And that type of system will produce fluctuations in brightness that can be fairly periodic. And so some of the variable stars, I don't think any of the ones we're looking at would fall into this group, but this is a type of variable star that would be a binary system. So you're basically seeing as the mass from the puffed up star falls onto the very dense star, eventually it, on the surface, it's causing these pulsations in light as it causes these explosions on its surface.
Kevin,
Mhm.
so after this star, should we go to the transients?
Sure.
So I have them in order.
Oh, okay, perfect. And I should make coffee soon. Also, yeah, Ken, thanks for these questions. These are great.
So for the transients, I think we should do the first three and then go from like 9 p.m. to 11 p.m. and then we can go to Andromeda and then go back at like 4 a.m. to do the rest of the transients.
Okay.
Okay, yeah.
Yep, sounds good to me. Good plan. Ken's next questions, yeah, no need to apologize. Happy to answer as many questions as you've got. But the question is, how many novae or supernovae have been studied in Andromeda since it was known to be another galaxy? I definitely don't know the answer to that. Maybe Monica does, but she needed to step out to move from her office to home for the night. Maybe Raja does, but I don't know. There's got to be, a lot. Sorry, novae, lots. Supernovae, not many. The interesting thing about this question, though, is it was in the argument before we understood what galaxies were, and it was this debate of whether the Milky Way and all of the things we see are just one galaxy, or whether these shapes we see in the sky like Andromeda, were they separate galaxies of their own, which we know today to be the truth. But part of the argument in that debate was the use of supernovae to say, oh yeah, no, these things, that light is shining like crazy. It has to be very far away. It has to be its own distinct thing. So supernovae in other galaxies was used as evidence to say that there is, we're not our own. There's not only one galaxy, but I don't know the number that we've seen. I don't know, because I always forget the rate of how many supernovae you expect inside of a galaxy, but it's not a lot. I think like a single galaxy should only have one supernova per 100 years or something like that. Raja, if you're here, maybe you could weigh in on that, but that's the number that sticks in my head. So let's stick with that. So, I don't know how many have been observed in Andromeda. Better question. Can you tell the rotational velocity by studying the shift in the spectra? By rotational velocity, do you mean the rotational velocity of a galaxy or the rotational velocity of a star? Yeah. This is work that, so the rotation of the galaxy, yeah, you can measure the rotation of a galaxy by studying the velocities of the different stars in the galaxy. And this is work that Raja and some of his students work on. They do a lot of studying velocity maps of Andromeda and other galaxies in our neighborhood. And by measuring individual velocities of the stars and then putting them on an image, you can see that some of them are moving one way and some of them are moving another way, which shows up as basically a rotation. Great question. Okay, we are reading out on red. I am sending new coordinates to POCO.
I have them
Okay, and we are ready to move.
on the way.
Okay, we are going to a still relatively bright target, like 16 or 17.5 magnitudes. I don't think we confuse it for anything else. And I have a
target.
Yeah, I'm just getting it for you now. Come on. Okay, I have a PA of 182.
182. Are we really there? You may set your slit.
That's the right one. There we go.
And you may begin.
Yikes. Messed that up. Ken, if you're still here, yeah, it looks like you are. This is an image from one of the papers that one of Raja's PhD students worked on, or like previous PhD students worked on for her thesis, where they were measuring stars in Andromeda. So each one of these, there's an artist rendition in the background, but each one of these colored points here is a star in Andromeda, where a different telescope, I believe this would have been taken with the Keck telescope on Mauna Kea, took spectra of each one of these stars, and then measured the velocity of each one of those stars. And then when they plot them in the space on the sky, and then color those points by their velocity, you can basically see the rotation. You can see that some of the stars are coming towards us faster, some of them are moving away from us. And if you do this across the disk, you're able to see the rotation of the galaxy. And this paper, I think, was looking at, yeah, you can see it in the headline here, that it was used to talk about how Andromeda had a more violent past than the Milky Way in terms of how it was assembled over time. So that's some fun connection there. That was when you Google velocity map of Andromeda, it comes up with research that Raja's PhD students have done.
Another point that might be made is if the galaxy is sufficiently far away, you can actually lay the galaxy along the slit of the spectrograph.
Yeah.
And see the rotation curve come out in the spectra.
That's a very good point. Yeah.
Doesn't work with Andromeda because it's too close and therefore too big. But
right.
Something a medium distance away, you can actually see it in the raw data.
Yeah, exactly. So what that would look like is here we see a single stripe here that corresponds to the the thin pinprick of light from the star. It's spread out a little bit just by the Earth's atmosphere and other effects in the telescope. But if you instead had the light from a galaxy, it shows up as a more wide brick of light all the way along. Still a stripe, but a wider stripe. And what Dan is telling us is that sometimes you'll see on one side of the center line here, you'll see basically features shifted one way, and in the other stripe of the line, you'll see features shifted the other way that are exactly because of the rotation of the galaxy. We'll bring this image back up here. Ken, I'm not sure exactly what question you're asking. You're saying why is the rotation similar for stars close to the center and far from the center?
Flat rotation curve. I assume that's what Ken means. Rotation speed being the same?
I'm not sure, because we were looking at Claire's figure here, and I'm not sure in the context of that what the question means. There's a background picture here that's like I don't know, it's either an
Herschel image. It's a dust image.
Herschel image. So it's an image of the galaxy that's maybe making things a little bit less clear because there's orange data points and then there's also this orange background picture. But if you ignore the background galaxy and only focus on these circular dots, this points closer to the center over here, to me, have a different color than the ones that are further away, which means they have a different velocity.
So Kevin, how I would interpret this is if you march, certainly if you go to the minor axis, which is what the points close to the center are, you're going to, that stuff, the disk is rotating, the rotation speed is perpendicular to the line of sight on the minor axis. That's why we get a blue color, which on this color bar on the right is -300, which is the velocity of Andromeda relative to the sun. But along the major axis of the ellipse, as you go further and further and further out, there's no dramatic change in color. It's a mix of oranges and greens.
Right.
It's sort of, if you look at the color bar here, it's a value of about -100 or so. Yellow is sort of a middle color, and you see two colors on either side of it. And the yellow, -100, is 200 different from the minus 300. So
Right.
the projected velocity on the major axis is about 200. It doesn't change rapidly with radius. You can see that it's, sort of reds and greens in the inner part, there where your cursor is, and then it's still, sort of reds and greens in the outer parts
Right.
as well. It's not, there's no blues. It doesn't become all red, it's a mix of oranges and greens with yellows thrown in. And that's the flat rotation curve of Andromeda. And like every self-respecting galaxy, it has a flat rotation curve. And that's because as you get further and further out, you're getting further and further away from the gravitational center, but you're including more and more dark matter interior to you, and they cancel. Those two effects cancel. M divided by R. So V depends on M divided by R. So it turns out that V squared is dependent on M divided by R, where M is the mass attracting you and R is how far you are from its center. And it turns out M over R is roughly constant for big galaxies. That is, the massive dark matter increases roughly linearly with radius. It's some K times R, so M over R is just K. So that's what flat rotation curves are. It has to do with the dark matter density profile, how much the density falls off with increasing radius. I don't know if that's what Ken is after with the question. That's what I'm thinking of.
Yeah, I got a yes in chat, but I'm
Okay.
not sure at what point we answered the question, but it sounds like we did at some point.
Good. Thanks,
Yeah.
Ken. Thanks. That's a
Perfect.
good
Yeah.
question. It's a good question.
Yeah, great questions from Ken. One of the ones that I didn't know the answer to, but I suspect the answer is 0. But how many supernova have been studied in Andromeda?
A lot of supernova remnants have been studied in Andromeda.
Right.
That is the remains of the explosion. But as far as actually watching something explode, I'm not aware of any.
Yeah, a supernova is so crazy bright that it outshines the galaxy. A single supernova outshines the galaxy that it's inside of. So one star is temporarily brighter than the entire galaxy. And so we have historical records going back to the 1400s when a nearby big event happened, the Crab Nebula. That's a supernova remnant, and that was a crazy event that everyone recorded. And if we saw something similar in Andromeda, it'd also be very striking. It would probably have been something that would have ended up in the historical record. And so I'm just going to go off and say that probably we haven't seen any supernovae in Andromeda in like recent human memory in the last few thousand years. Raja, you're muted if you're yeah.
So the one in the Crab, that was, I think, 1000 or 1050 something AD. So
Okay,
that
not
was
1400.
Yeah, so it's not quite 1,000 years ago, but close to that. 900, more than 900 years ago, and that but there was a supernova in the Large Magellanic Cloud in 1987. There are supernovae happen. It has to do with not just how big the galaxy is, but also how how vigorously it's producing stars, because it's the youngest stars that explode. Sorry, it's the most massive and short-lived stars that explode, not the youngest, but the most massive and short-lived stars that explode, most frequently. Yeah, I don't know. I mean, so Emily's boyfriend, Zach Jennings, before he came to Santa Cruz, when he worked with Julian at the University of Washington, he was studying supernova remnants in the FAT survey data.
Cool.
So these are the remains of exploded stars rather than the explosions themselves. The remains stay around for a very long time. The explosion is bright for only a week.
Question for you. I couldn't remember the exact number, but it's what is the expected rate? It's 1 supernova per century in a galaxy like the Milky Way.
That's right, something like that. Yeah.
Okay, that's what I thought.
But it depends on its star formation rate, and Andromeda's star formation rates are relatively low. It's not forming stars very vigorously because of all its interactions, etc. But it's a good question. Why haven't we seen any in Andromeda?
As we keep blinking.
Is it? Yeah, we keep blinking. Austin has asked, is there a way to predict supernovae or observations that lead up to one? Well, really massive stars, you can be sure they'll end up as supernovae. The thing that's hard to predict is when they're going to explode, because these stars live for millions of years. They don't live for tens of years, hundreds of years. So predicting something with high precision, it's like trying to forecast the end of a storm that lasts a million years long, right? I mean, when is it going to end? Even if you get it correct to 10% of its life, 10% of 10 million is, you're uncertain by a million. Or if it's a million, 10% of a million is 100,000 years. That's your sort of precision level. So it's hard to know when something is going to explode. It's very clear that many of the stars we see in our Milky Way galaxy are going to explode. Many of the ones we see in Andromeda are going to explode. We can be sure of those. But exactly when is much harder.
But at the same time, there are some telltale signs that something interesting is going to happen relatively soon if you're looking at a star. And this is a very open question, is trying to understand the lead up to supernovae is very open, and different types of supernovae. To try to understand progenitors is active research that some of the people in the Santa Cruz department spend most of their time thinking about. But I think in the news you'll sometimes see, which one is it? It's not Barnard's star. It's I think it's Betelgeuse or something. People keep saying it should be exploding soon, but who knows what?
Betelgeuse is exactly the one that people are worried about might explode.
Right. Yeah. So there's telltale signs that something's nearing the end of its life.
There are pulsars that are quite close to us, Ken, and I'm not a radio astronomer, but those who study pulsars, there are pulsars that are relatively close to us. In fact, some of the early pulsars that were discovered by Jocelyn Bell and Tony Hewish were relatively nearby pulsars. The technology of that time was such that you could only see the brightest and nearest ones. Depends on what you mean by close, of course, but pulsars tend to be, they tend to come from neutron stars. They tend to come from massive stars. So they tend to be associated with the thin disk of the galaxy. So they tend to have distances of 100.
1 second, Raja. We are reading out on red. I am sending new coordinates to POCO, and we are ready to move.
Okay. I might also note that somebody is dragging something against their microphone, and it's a little distracting.
Okay.
Okay, and we're on the move at 2032. Going 102 east. And do you have a PA for this target?
Yeah, just give me a sec. Sorry, I was trying to decide if it was me who was the microphone abuser, and I think probably.
Our guider image looks so much like Jupiter right now.
Which is funny because when you look at Jupiter, it doesn't look anything like Jupiter.
Okay, I have a PA of 154.
154.
Austin, no need to apologize for any of the questions. We're happy to have you, and there's no reason to think any of these questions are elementary. We're happy to go back to whatever level people want to talk about things.
Sometimes seemingly simple questions reveal profound truths also. So
Absolutely.
can I have the slit narrow, please?
Yes, my bad.
Thank you. Now, what I'm going to do for a guide object. Okay, you may set your slit. And you may begin. Before we get back into the physics, I'm going to recommend that we make a focus check on our next slew.
That sounds good. Thanks. Ken, it's funny how often when we find new physics, the answer everyone wants to jump to is aliens. Pulsars are little green men, and there's no way the universe could make a signal so regular. Or the that meteor or the comet that came through the solar system a few years back that some people are still insisting couldn't have been shaped by natural processes.
Oumuamua, that one.
Oumuamua. Yeah, Avi Loeb really is convinced. Yeah, the flying cigar.
And Tabby Star had everybody convinced for a while that somebody's building a Dyson sphere. So
Right. Okay, I'm going to step out for a bit. We'll be here for another little over 10 minutes. I'll say 12 more minutes. I'm going to go make some coffee and be right back.
Raja, I think there's a question for you in the chat.
Stephanie, I tried to answer it in the chat about this disbandment of galaxies. Yeah, the most common way for galaxies to die, if you like, or get destroyed, to lose their identity, is to get swallowed by something bigger. Because stars live for the, especially low mass stars, live for a very, very long time. And the big rip, is fine on large scales, but on galaxy scales, dark matter wins over dark energy on galaxy scales. That's what gives a galaxy its identity, and that's what holds things together in a galaxy. It's the fact that dark matter is winning out over dark energy.
Okay, so we're gonna do a alignment check or a seeing check right after this.
That is the intent. The question is our next target going to be closer to zenith, or shall I find a nearby object here?
I have a RA of 2347. So I guess we're
the
closer
deck?
now.
What's the deck?
It is 2427.
And your RA was 23 what?
47.
It's going to be about the same either way, I'd say.
Okay. Well, yeah, go ahead and just pick a bright thing nearby if that's easier then.
I'm working on it. Are we ready
worries.
to move at this point?
No, we're still reading. Okay, now we're reading out on red, so we're good to move. Do you want me to narrow the slit for you?
Yes, please. Okay, so did I hear you correctly? We're ready to move?
Yeah, we're ready to move.
Okay. Oh. That doesn't seem right. They lie. This is nowhere near 9.5 max star. And Kevin, I think your mic's being brushed again.
Ah, it's not me. I was muted.
Okay, so everybody check yourself for dragging objects.
I wonder if it's me, but I haven't, nothing has changed, and I can't see that my microphone's rubbing against anything. But I'll be careful. I'll see. No one else is unmuted, so it would have to be me then. But the last time you said it, I was muted.
So I keep hearing things going across the mic. So it might be something blowing, it might be something dragging.
You're not hearing it now, right? I assume.
That is correct.
Okay.
Interesting though, because I don't hear anything, so I'm not sure.
Are you hearing it now?
Right there.
Okay, that must be my microphone rubbing against my shirt. Okay, I'll be careful.
Thank you.
Sorry about that.
Not a big deal. Just, it distracts a bit is all.
Yeah.
So, okay. I'll do the calculation later. Go ahead and send your target, Kevin. On the way.
Perfect. And this one should also be fairly isolated, so.
And do we have a PA for this?
Oh, right. I was supposed to be calculating that. I have a PA of 131.
131. Okay. You may set your slit. And you may begin.
Perfect, thanks.
And updating the seeing estimate is approximately 1.6.
Hot dog, that's a lot better than it was before.
Yeah, it looks better, doesn't it?
Yeah. Rajah, I don't think you heard the first seeing estimate, but I think it was 2.4 or something.
Wow. Wow.
That's what it's recorded as here in the logbook, 2.4.
Yeah. But it was also like the temperature was still, or the telescope was still cooling down and stuff. So
Sure. Beginning of the night.
Yeah, we still had a pretty big split between inside and outside too.
Got it. When I hold my microphone like this, hopefully you don't get any of the brushing sound.
Yes, it's much clearer. Thank you.
Okay, thanks.
And then there it is a couple times.
You heard it again?
Just a couple times there, yeah.
I don't know what is going on because now it literally is not touching anything.
It may be that something is dragging across something else close to the microphone without actually touching the microphone.
I can't imagine what it would be. There's literally nothing here.
Yeah, welcome to the world of troubleshooting.
I know. I think the best way for me to troubleshoot is to mute.
Hey, Kevin.
Hey,
Hi.
Monica, you back home?
Sorry, it got longer than I expected.
That's okay. We've been doing good here. Got a few transients. Did a seeing check. Things are looking better than they were earlier.
Nice.
Yeah, we're on to our last of the first half night transients. Then we'll go back to M31, and then we have a few more at the end of the night.
Oh, nice. So
The,
this is not the so we are done with the AGN, and we're also doing more of those transients.
I don't know which one's the AGN.
Yeah, this is the AGN.
Oh, right now? Okay,
Just looking at the object ID.
perfect. Cool.
So it should be noted that we've got a little thin cloud coming through at the moment too. So it's easier to see on the black and white all sky.
There we go. Yeah. Okay. Yeah. So long as we don't lose guiding, it's bright enough that I'm
Yeah,
not too worried.
based on what I'm currently seeing, I don't anticipate any problem with guiding.
Okay. Yeah, it's bright enough. We can always do another exposure if we need to or something.
When you have too many AGNs in the sample, you call it this. I put it in the chat.
Alrighty.
Agency.
I'm noticing that the stream of questions has died way off. So have we lost our audience at this point?
No, we've still got a few
people,
observers.
and there's a group of students from who will be connecting from Zambia and Zimbabwe at midnight our time. So it'll be 9 a.m. for them.
Ah, okay.
But this group that's here is mostly there's a collection of it's a combination of UCSC folks and Hawaii folks.
You get some broad features here.
That looks like an AGN bump there.
Yeah. I can see it on the 2D spectrum too, right here. And then it probably also something else right here. Let's go look at the blue side. Harder to tell.
Harder to tell in the blue, yeah.
Yeah, ignoring that. Yeah, the red side has some cool features.
Charlie, that's not a beginner question at all. But what you're looking at in the red window there is the x-axis, as you can think of it as the color of the light or wavelength of the light. You know, light is can be thought of as waves, and those waves have different wavelengths or frequencies. And that frequency or wavelength is the quantity on the x-axis, and the y-axis is how much energy is coming out at each wavelength. So in a sense, it's a measure of what kind of light is coming out of this astronomical object. This happens to be something called an AGN, active galactic nucleus. That's what you're looking at. The significance of the day, we don't quite know yet until we can identify exactly a pattern. And I certainly can't just looking at this section of the spectrum, but that's one of the things we'll get to do later. That's a very good question. It's not a beginner question at all.
To just expand on what Raj is saying a little bit, what we do at the beginning of the night, that maybe some of you tuned into, is we do a lot of calibrations of the telescope, so that we're able to take these pictures here, these 2D images. You know, this is like something a picture you take with your phone almost, where each one of these is a pixel and it's just recording light. And then later on, what Stephanie does is she uses some software that tries to identify the columns here of light that are associated with the star. It tries to remove these stripes here that you're seeing, these horizontal stripes that are actually from the Earth's atmosphere. So it's the sky is glowing at a few different stripes here because there's molecules and elements in the Earth's atmosphere that are interacting with the light as well, and they're radiating their own light signal, which produces these stripes here. So that's one thing we need to remove. And then also one of the things we do at the beginning of the night is we take arc lamp calibrations. And so basically we take a bunch of tubes that are filled with known gas, very pure gas, and then they're electrified so that it makes light from those elements. And so these are like tubes of neon or tubes of mercury, and they produce very well-known wavelengths of light all across both the blue and the red detectors. And so every stripe that we see, we know exactly what wavelength that occurs at, and then we can use that those calibrations to help us figure out later on this pixel corresponds to this wavelength of light. And so one of the things we'll do later is use all of that to figure out where this feature occurs, which tells us what wavelength this occurs at, which tells us what chemical we're looking at, and that helps us make our inferences about whatever star or galaxy we're looking at. Oh, and I guess I can just bring up one of those images. If I go, let's see, probably one of the first ones. Yeah, so this is, these are some of those arc lamps. It's a little bit messed up, but you see this barcode pattern. I don't know off the top of my head what each one of these corresponds to, but if I take okay, if I take a slice here, you see a bunch of spikes that correspond to particular elements. So if I zoom in here, I know that these two peaks are from, oh, now I'm going to embarrass myself. They're either mercury or cadmium. I can never remember which. And so I know exactly what wavelength this is at, and I know exactly what wavelength this is at when I go and run it through my software. And so I can tell later on I can say, oh, this pixel over here corresponds to that wavelength. And then I can play that game with each one of these peaks, which when I go back to my real data allows me to turn things into, instead of light as a function of pixel, I can turn it into light as a function of wavelength. Okay, we are reading out on red, and I've sent new coordinates to POCO, and we are ready to move.
And we're on the way at 21:15.
And I have a P89.
8-9er?
8-9er. It's an 18th magnitude star. Should be isolated enough that we should be able to get it
Hope so.
without a finder chart, because I'm lazy. I think you've got it.
Yeah, I'm just double checking the field. I'm always suspicious when it drops right on the crosshair.
Yeah, I appreciate the double checking.
Well, I think this qualifies as the easiest acquisition we're likely to see today.
Perfect.
Let's see, what's our cloud situation? Could be better, could be worse. You may set your slip. And you may begin.
Okay, and we will be here for 40 minutes.
I'm gonna step out and have a look at the sky and make sure there's nothing sneaking up on us humidity wise, and I'll be back.
Perfect, sounds good. Monica, did you see the AGN readout?
Sorry, Kevin, could you repeat that?
I was just wondering if you saw the AGN spectrum.
Yeah.
Yeah, okay, just checking.
Yeah, I think so we might have to check this, but maybe the narrow emission line has disappeared. I may be wrong, but I think there was so for the Balmer lines, there's generally a broad component, and there's this narrow line sitting on top of it. So for this one is you have it at 7. So this is H alpha, or
I don't know what this is. It's very far away from where H alpha is in rest frame. So like it's down near, oh, I didn't mean to do that.
But that would be its redshift, of course. That could be.
Yeah, I just don't know how much to expect it to be redshifted by. But if we
And
think it's,
is wavelength running increasing to the right or left on this one?
this is very redshifted.
No, but I mean, is wavelength increasing to the right
Yes.
in this red graph?
Yes, yeah.
Increasing to the right. Huh.
Mhm.
Because, you know, normally these broad lines in quasars have this sort of P Cygni profile. That's what I would have said this
Right.
one is, but it has the wrong, you know, they tend to be sharp on the blue side and shallow on the red side, but this is the other way around. It's shallow on the blue side and sharp on the red side.
Yeah, and in case you're curious, H alpha rest frame is right where my cursor is.
Okay, but this, so it could be redshifted H alpha.
so where your cursor is, that is the rest frame. No, that's H alpha.
Rest frame.
Yeah.
Rest frame. Okay.
Approximately rest frame. I'm basing this off of other stars, but stars, you know, they're not moving that fast.
Yeah.
Yes. Go on, Stephanie.
When are we doing the standards?
Oh, good point.
Yeah,
Right.
need them.
Let's do them right after this.
Yeah, makes sense. I guess the RA might be right on with the LST right now. So thanks, Stephanie.
No problem.
Yeah, they're at air mass of like 1 HAs of half an hour. Also, I just based on the amount of exposure time we were the remaining transients, I put a little note of the start and stop times for basically the end of the night, because the 18-degree twilight or dawn starts at 5:45 local time. So we'll start the end of the night at like 3:40. We'll head over and start doing more of our transients, which works out pretty well, I think, with when Andromeda is starting to set. So that'll be good.
Yeah.
I'm going to step away for just a couple of minutes. I'll be back.
Yeah, okay. Be here for a while. I'm also going to step out for a bit. Gotta put a mattress on the curb so that the large parcel pickup people will get it tomorrow.
Kevin, are you back in California though?
Yeah, no, I've been back here for a while. Yeah, I was home visiting family for mid-August to mid-September, but I've been back since mid-September. I'm actually going to go back and visit family for the weekend, this weekend. So back to Canada.
Nice.
Okay, I'll be back in a little bit here.
Yep. Stephanie?
Yeah.
So can you confirm me? I just got a bit confused. The exposure time 800, that is for a single exposure on this target.
The exposure right now.
Yeah. To be 800.
That one is. Yeah, that one's supposed to be 2400.
No, this is for the AGN.
Oh, for the AGN.
Super bright. Oh my gosh, that's 800 times 3. That's 24. No. 800 was supposed to be the total. We had to split it up into 300 times 3.
Yeah.
That's super bright. So I mean, it's fine with, it's not going to be saturated, but we are spending more time than is necessary on this very bright target. It's around 16th magnitude.
Yeah. Well, for the AGNs, we only did we only did 300 exposures 3 times. I think I accidentally put 900 on the list.
No, okay, okay, this is not the AGN then.
No, this isn't the AGN right now. This is a variable.
Okay, good.
Yeah, for the AGNs, we did 300 second exposures 3 times.
Oh, okay, so all right, so with the it's good to know. I'm relieved.
Okay.
Okay, so that's just total of 900 seconds. All right, all good.
Okay.
I'm like, okay, so this is the second exposure on the AGN, and I just got.
No, yeah.
Yeah,
So it goes like early on. Yeah.
Okay, awesome. All good then. Thanks.
I'm back.
I think there's a question in the chat about dark energy.
Oh, yes, I see this. Austin with the deep, deep questions.
Yeah.
I mean, the dirty secret about dark energy is who knows what it is. It's one of the, I'd say, most open questions about the nature of our universe. It's, we don't, I don't know, we don't know almost anything about dark energy.
That's why it's called dark.
Yeah. It sounds like it's related to dark matter because it's also got dark in the name. But in both of those cases, dark just refers to the fact that we don't know much about it, if anything. And we know a lot more about dark matter than we do about dark energy. So if you look at kind of like a pie chart of all of the matter in the universe, and we have to remember E equals mc squared, so matter and energy are the same thing, or different versions of the same thing. If you look at that pie chart, only 5% of the universe is baryonic stuff. So this is the stuff we see and what we normally think of as matter. And then about 30% of that pie chart is dark matter, stuff we can't see, and we think we have some ideas about what it is, but it kind of interacts with the stuff that we see gravitationally anyways. And then dark energy is the other, whatever the math works out to be, 65% or 70% of everything in the universe as we currently understand it. Basically, the way I understand dark energy is it's kind of a mathematical anomaly, or not anomaly, but in writing out Einstein's equations of general relativity and trying to explain the laws of the universe and gravity on large scales, we need an extra term in there to make everything work out. And this shows up as an energy term, or sometimes called like a negative pressure term or a vacuum pressure that explains the expansion of the universe that we see. So very far away things are expanding away from us faster than nearby things. The expansion of the universe, things are expanding away from each other, but things that are farther away are expanding at a faster rate away from us than things that are nearby. And the way that the math works out requires this energy term, this dark energy term, to make everything work out. And so what that actually is and how to think about it is a little bit complicated. I don't have a really good sense of it. I kind of think the way that I think about it is there's some like kind of outward force that the vacuum of the fabric of reality has, and it's not until you're looking at very large scales does that add up to an effect that we can see, where things are, it causes things to move apart faster than they would otherwise. Raja, do you have anything to add to that? Monica?
Well, no, I think one of the big questions, and I think one of the big differences we think between dark matter and dark energy. By the way, they're also called dark because they don't interact with light and produce light.
Right.
We are in the dark about them, but we're in the dark about them because we use electromagnetic radiation to study the universe. And since these things don't produce any electromagnetic radiation or interact with it, it makes it very hard. And those two things, they're called dark for two related reasons. They don't put out light, interact with light, and that's what leaves us in the dark. But the other thing is, dark matter clumps on galactic and on the scale of individual galaxies and clusters of galaxies. Dark matter is thought not to clump. It's thought to be, it has a certain density in the universe at a given cosmic time, and exactly how that changes with cosmic time is a subject of debate. That's called the equation of state of dark energy. But it's not thought to cluster in space. That it's not meant to be, its density, that is the amount of dark energy per unit volume, is not thought to be variable with position in the universe. And that's a big difference relative to dark matter. The Milky Way galaxy we live in, Andromeda, these are concentrations of dark matter, where the effects of dark matter are greatly outdo the effects of dark energy. Because what happens is when something is uniform, then there's as much tug as there's push. Those things sort of balance out. Whereas, and that would be true if dark matter were completely uniform. You would feel an equal pull in all directions, and you'd feel no net force. It's really the clumping of dark matter that is super important here. Anyway, I'm repeating points that you've covered, Kevin.
But yeah, these are very open areas of debate. I think as we get closer to nailing down exactly what dark matter is, I think that'll help us in our goal of figuring out what dark energy is as well. And there's camps of people out there who are arguing that maybe we just don't understand the physics, and maybe because we haven't found dark matter, it maybe means that our understanding of physics is incomplete, and so people are proposing different models that would explain, what dark energy is without having to think of it in the way that we think about it now. So yeah, these are very, very open questions that telescopes are being built to explore, like right now, or are coming online right now, are going to be taking measurements of everything in the sky as much as they can to use statistics to basically understand things on all scales to try to answer these questions. So it's an exciting time. I think in the next, I don't know, the number I always hear thrown out is 10 years. We should hopefully know what dark matter is. And it seems to me that would help us on our goal to understanding what dark energy is as well.
Yeah, yesterday I was on the phone with one of the three people who got the Nobel Prize in Physics for the discovery of dark energy. I had a long chat with him yesterday.
Who's this?
Adam Rees.
Oh, okay. Yes.
In fact, I sent an email to Brian Schmidt today, one of the other Nobel Prize winners in that group of three. And I know Saul very well, but I haven't emailed or called him in the last few days. Yeah, but I needed to reach out to those two people for the same reason.
Okay, we are reading out on red. I am sending new coordinates to POCO, and we are ready to move.
If I can ever find my mouse, there we go. Oh, looks like a standard.
That it is.
We are moving at 2159.
And I have a PA of 3-5.
3-5. Just waiting on the dome here.
No worries.
You may begin.
Thank you very much.
Hey, Sarah, I'm so glad you've joined. Thank you for advertising this.
Okay, I am done with this standard, and let's go to our blue standard next, sending new coordinates to POCO, and we are ready to move.
On the way.
I have a PA of 6-1.
6-1. You may begin.
Thank you.
Um, Arya, I'm trying to answer your question in the chat.
Drat. Did I leave something off the observing log? Yes. Okay, I can fix this. Okay, we are reading out on red, sending new coordinates to POCO, and we are ready to move.
On the way, 2211.
And I have a PA of 7-6.
76.
This one's going to be pretty faint. Let's see. It was last at 18.8 mags.
Well, do you have a backup plan if we can't go direct?
Yeah, I was just going to try and see if the area was crowded or not, but it's not loading. So I'll probably just make a finder chart real quick.
CTF 18ABUG.
For those watching at home, sometimes your target is faint and hard to find with the telescope. And so we'll download a historical image and then we'll use the nearby bright targets to define offsets to our target. So our target is at the very center of this image, which is very hard to see. And so I'm going to give coordinates offsets from that to some of the brighter things nearby. So it's
Yeah,
easier
before you get
to.
too busy with that. I can believe that's in the very high 17s.
The high 17s. I don't. The chart isn't loading for me, so.
But I don't see anything in the historical image that's that bright.
Okay, I'm gonna be safe and just send you the offsets.
Okay, guess that means I need to fire up my email. I'm going to proceed on the theory that that's it.
Okay.
And if when your offset finder gets here, we can try a reverse offset.
Sure. It's on its way to you now.
Google just get their act together. Wake up. Nope. Still nothing.
Really? Okay, mine's stuck in the outbox. I've been having internet issues.
Well, I was
Strange.
trying to look at a YouTube link earlier, and YouTube was having significant difficulties, and Google image search is also having trouble. So I suspect Google is having a little hiccup.
Yeah, that seems right. Yeah. Let's see if I can just cross match by eye. So in my image,
I can go back to the large view.
yeah, that'd be helpful.
So. Okay, here we are on 2 seconds of integration. This is what I believe is our target. We got a bright object to the south-southwest, these three to the east-northeast, this triangle with these two pointing almost directly at the crosshairs in the historical image.
Shoot. Yeah, I just got a UCSC server failure.
Oh,
So
nice.
The email did not go through.
Well, I think we're doing this the old-fashioned way then. This is the correct field.
Yeah.
I will state what reputation I have on it. And the fact that these two, which show up in the historical image, point directly at the center of the crosshair, which
Yeah.
is, give me pretty high confidence this is their target.
Yeah, it's just surprisingly bright. Maybe that last measurement was a while ago.
And your little pointer finally turned up.
Hey, there we go.
So, go make sure it's still in the center of the slit. And I believe that the, I did not tell you to move. I believe that this item here is blue.
Yeah.
And this is green.
Yeah.
So we
did it.
if we go 14.8 east and 22.59 south, that should land us on blue, which it does.
Perfect.
So, oops. All right, you may set your slit. And you may begin when ready.
Perfect. And we will be here for 40 minutes. Or, oh, we don't need that long, I guess, if it's brighter than we thought. I'm going to say 30 minutes then.
I will also say that seeing seems to be improving still, so that's a happy thing.
Yeah, we never get that.
Every now and then you get lucky. And I think you're having a John Wayne day, so.
It's a pretty faint trace, so I'm gonna bump it up to 800 seconds for the next two exposures.
Casey, take care and stay in touch because that project you're working on with Yuting is about to heat up and we need your help.
Definitely will. I've got all
Okay.
the notifications on and everything. So
Got it.
No, sorry, we are reading out on red, so I'm sending new coordinates to POCO, and we are good to move.
Okay, and I assume the finder that just came through is for this?
Yes, yeah, it's pretty faint, so I figured let's be
Yeah,
safe.
better be safe. So
Yeah.
we are slewing at 2258.
Perfect. And I have a PA of 2.7.
27. Is that correct?
Yes.
Right. So 207, here we come.
Okay. I'm gonna change the PA since we're gonna do such a long one on here. That's the current PA. I'd rather do an average. We're gonna be here for so long. Could I change the PA to 158?
Going back the other direction.
Yeah, I'm sorry.
Oh, I just wish you'd announced that 15 seconds ago. It would have just sped things up a little is all. 1, 5, 8. Okay. I don't know what, where now? Oh. If in doubt, got it the right way around. Well, there's been a lot of people coming in and out.
Yeah.
Screen.
Yeah. So we're we'll have a group coming in a few minutes from Africa. 2 groups tonight.
It'll be interesting to talk to a different continent for a change. So what is your expected brightness on this?
Like 18.8.
Wow. Either seeing has gotten incredibly good or this thing has brightened up on you.
I hope it's the first one.
So do I, but I'm reasonably confident that that's the object there in the crosshairs. We can do a reverse if you like.
Sure, yeah, better safe than sorry.
Okay.
But I think you're right.
Set this up. And we'll go 50.2 west. 38.39, 38.39, I said. North. That should bring that. That drops it on something that sure looks like green.
Perfect.
Go back to target. Yeah, I think seeing is finally decided to settle. It's helped by the
Right.
fact that mirror temperatures have been more or less constant for the past 2 hours.
Right.
So,
What do you think 1 arc second or maybe even sub arc second?
I don't think I'd go so far as sub-arc second. Probably very close to 1.
Okay. Yeah, I think I've only had sub arc second once on Lick.
You know, if we wanted to spend the time, we could double check that, but that's,
Nah, it's okay. Did I narrow the slit for you?
you did.
I did.
And I'm about to tell you, you can widen it back out.
Perfect. About to tell me, or I can do it?
You can, in fact.
Okay.
And you may begin.
So the different groups from Zimbabwe and Zambia should be collecting anytime soon now. It's midnight here. So it's 9 a.m. for them.
So they're all bright-eyed and bushy-tailed.
Their school day is just starting. That's right.
DZVPR.
Bernie asked about the position angle change. I wrote an explanation. When you get a chance, please
Yeah.
tell me if I got that right.
That's perfect. Yeah. So for those who aren't looking at the chat, I changed the angle that the telescope is rotated on the sky, because as the light passes through the atmosphere, different wavelengths of light get bent by different amounts. Just like in a prism. And so when we're looking at these really faint objects, it's important to not lose any light. Otherwise, we need to take a longer exposure and we're wasting time. So we like to orient the telescope or the slit of the telescope, this thing here, so that we collect all of the light. And so that's the parallactic angle we're calculating. And so because this is it changes depending on where you are on the sky, and things are moving across the sky throughout the night. If we're taking a really long exposure, I can either choose the parallactic angle at the beginning or the parallactic angle at the end, or in this case, I chose the kind of the average parallactic angle throughout the 50-minute exposure that we're doing now.
So 2 things real quick is, 1, it's actually the instrument that you've rotated, not the telescope.
Okay, my bad.
And 2, it might illuminate people to know that the parallactic angle is basically we're putting the slit perpendicular to the horizon.
Mhm.
For the same
Right.
reason that sunsets are bright red and multicolored as the sun goes down. The atmosphere diffracts, as Kevin was saying. And so what we're trying to do is capture as much of that diffracted light as possible.
No sense in losing photons, especially with all these really faint targets.
You pay a lot of money to get these photons. There's no sense.
Yeah.
Yeah, one way to think of it is the atmosphere produces a tiny little spectrum of each star. Basically, the red light from the star lands in a different part of your retina than the blue light because they bend by different amounts when they come through the atmosphere. They basically form little vertical ellipses, and you want to orient the slit vertically so that light of all colors comes through the slit, whereas if it were horizontal and you're creating a vertical ellipse, that means only light of certain colors gets through the slit and the rest of it gets blocked by the metal.
Yeah, before I started learning how to observe, I think I naively thought it was just as simple as, you point your telescope where you want to go and you open a shutter and then you take your measurement, then you're done. There is, so much engineering and thought that goes into every step of the process, more so than I definitely realized at the beginning.
to be fair to you, for a direct imaging telescope, that's what you do, is you point it in the direction you think your object is. And for photometric measurements, you take a picture and you put a filter in of a various color, and you take another picture and put a different filter in, and then
Right.
you compare how bright the images are with the different filters, and that tells you something about the color of the object.
Right.
What we're doing is somewhat different.
This is true.
Uh,
Yeah,
I'll let you explain it, because if I explain it, I'm just going to confuse everybody.
sure. Yeah, and it's probably a good time to, well, maybe we'll wait a little longer as our African groups trickle in before we explain all the different things here. But yeah, we are doing something very different than something like Hubble that's taking a classic picture of the sky. We're taking a spectrum, just kind of like spreading light through a prism.
And people are very used to images because that's what we do with our phones all the time.
Right.
Cell phones, what we, when you point and shoot, you're taking an image. And that the detectors in your cell phones are not that different from the ones we're using here. They use slightly different technology, slightly different in the sense the pixels have different arrangement of, they create color, they take images in effectively 3 different colors at the same time, RGB at the same time. These CCDs don't do that. But so people are really used to images.
There's a question here from Bernie. Could you
Yeah.
design a system where the PA changes continually through an observation? And I feel like my naive answer is yes, but the only the only concern I'd think about would be like dark currents and stuff, and like whether that would impact your observation. But I don't know.
So I'll speak as an engineer, and it is certainly possible to design a system that would do that. In matter of fact, in other telescope technologies, the so-called altitude azimuth telescopes, they have what's called an image derotator that does actually sort of the opposite, which seeks to keep the image from streaking on the sky as you track. This telescope is a equatorial mount, and without getting deep into it, the advantage of the equatorial mount is the image does not rotate on the sky. So by designing something that would rotate the slit as you tracked across the sky, you would lose that advantage.
Yeah.
And
You're saying it would be easier to do a continuous rotation on an Altair telescope?
you get it basically,
Naturally, you get it
yeah,
naturally.
you get it for free on an Altair.
Yeah.
Here, the equatorial was originally designed for direct imaging, and the fact that we've got a spectrometer on it now means that if we wanted to get that rotation, we would have to go back and redesign some of the instrument.
Mm-hmm.
Right. Yeah, and I guess there's all the technical constraints too with this particular telescope in terms of like you've got to be aware of the wrap in terms of you can't pass through certain PAs and at certain speeds, and yeah, I could imagine as you pass through.
So the other
Zenith, things
danger
could get bad.
So the other danger, of course, I'm sorry, Kevin, I didn't mean to, you
worries.
cut out for a moment, so I thought you were done. Sorry about that. So the other danger of letting the sky rotate is if you have a slit spectrograph, even though your object of interest might be at the center of the slit, if you have a longish slit, different things, you basically form star circles around your around your object of interest. So other things could come into your slit, not on top of the object of interest, but they could come into other parts of your slit. So you would have you can imagine that the rest of the slit is picking up not a single location on the sky. So you get, it sweeps across, it sweeps in a circle across the sky. So that may be a disadvantage for certain things.
Yeah, I didn't think of that. So one of the things that we need to do later on when we're processing the data is remove the effects of the sky. And if you have things and especially if there were bright things coming into and out of the slit, it'd be much harder to define where the sky is and what the sky spectrum is so that you could subtract it properly. You'd have to have a fancier algorithm to
Yeah, you
properly identify it.
you generally get less blank sky, right? I mean, that's what
Yeah.
would happen. Yeah.
So if one of you would show the guider copy for a moment, it might help to show the kind of thing that we're trying to avoid. So here you're looking down in the sort of purple box there, you're looking down into the instrument from basically the sky. And if you see the little red box that I'm going to move, you see this is a star. And if you can imagine that the slit rotates relative to the sky, there's a possibility that star is going to go like that across the slit. And that's what they're talking about, having additional light from a different object that would make it more difficult to, as they call it, reduce the data to determine what they want to find out about the star they're actually tracking on.
Oh, that's a very good explanation, Sean, and good illustration here. And one of the things about astronomy is when we can point the telescope to a star, but we can't slice the light that's coming in terms of its distance. We get everything that's coming to us from that direction, whether it's in front of the star, from the star, or behind the star. And because of this, we take spectra through slits so that we can look on and off the star and hope to sort of account for this unnecessary but inevitable foreground and background light that the rest of the slit is capturing. See, so basically, if we cut a circle on a metal plate and pointed it to a star, that would not be good, because we would get the light of the star, we'd get the light of the foreground, we'd get the light of the background, and we'd have no way of separating these three things. Whereas if we cut a slit, we can look on the star and off the star, and it's a pretty good bet that the foreground and background are smooth across small patches of sky, so that when we look off the star, we're only getting the foreground and background. When we're looking on the star, we're getting the star, foreground, and background, so we can account for the foreground and background that way. And that's a process called sky subtraction.
Or that sounds like you're starting a fight with the fiber folks.
The fiber folks do this by having sky fibers. That is,
Right.
they pointed blank patches of sky for exactly this reason. And in fact, sky subtraction is harder to control for fiber spectrographs for exactly this reason.
Of course, now having mentioned fiber spectrographs, somebody's going to have to explain what they are.
Yes.
Yeah. Well, I think first we should probably explain what we're looking at here for the people who've joined us since we last explained all the different screens we're looking at.
And in fact, what I want to do is take a moment, Kevin, to ask the folks on the call to introduce themselves. Bernie, you've already introduced yourself. Arya and Austin, you have. But I was going to ask, I know we have folks from Irene Christian College in Zimbabwe who are connecting. I would love for you guys to unmute, turn on your video. Your video's on, actually. So, and introduce yourself. I also see Isabella, you've been on for a while. Jane, Knowledge is my good friend in Harare, in Zimbabwe. Perhaps we start with Knowledge. If you could please explain or introduce the folks who are connected from Zambia and Zimbabwe in the morning, your time. Knowledge, please take it away. Please unmute yourself and introduce yourself in the group.
It looked like Knowledge was moving locations.
Okay.
So maybe not the best timing.
Okay. Is anyone from Irene Christian College able to please introduce the group? Okay.
Good
Oh,
morning.
no, yeah, there's knowledge. Good morning. Good morning.
Good morning, sir. We're from Irene Christian College.
Hello, and welcome.
Hey, hi, guys.
I'm going to make your video a little bigger so we can see you better.
So that's just on your screen.
That's on my screen. Yes, I realized that. Yeah, I just want to make sure I can see people. I have my screen split 50-50 for the recording. So I was hoping to. How many students have joined from Irene Christian College?
14 students.
14. Oh, wow. And are you located in Harare or some other part of Zimbabwe?
We're located in Harare.
I see. I see. My name is Raja, and I'm a friend of Knowledge Chikundi, who's also based in Harare. And we worked with 2 students this summer from Queen Elizabeth School. Their names are Nokutenda and Ruvarashi. They worked on an astronomy and a project that's at the intersection of astronomy and art with some of my colleagues and myself throughout the summer. And I don't know if you heard of their experience, but they had a very good time. And may I know your name, please? Hi, the person with the microphone, please.
I'm Nakanaka Chawe.
Are you with the Irene Christian College then?
Yes, I'm the president of their science club.
Oh, fantastic. Welcome and thank you for joining. I know you're taking time away from your classes to take part in this. Your school day has started, I assume?
Yes, it has.
Okay, well, thank you for taking time away from classwork to join us. It's midnight in California. It's a little past midnight. It is 20 minutes past midnight here. It's 9:20 for you. It's a 9-hour time difference. And,
Yeah.
Is Irene Christian College a co-ed school or?
It's a co-ed school.
Okay.
Yeah.
And I think we have a second school joining today from Zambia, thanks to the efforts of Knowledge. How did you find out about this event?
Well, Mr. Knowledge was posting it on his status and it looked interesting. So I was like, our school definitely has to participate in this because it's an exciting opportunity for the students. So yeah,
Fantastic.
I contacted him.
We would love to explain what we're doing, but also we would love to take questions from your group, any of you, all of you. And let's see.
Well, once we finish the introductions, it might be easier to explain some of the things we're looking at, and then the questions might
will be easier then. Yeah,
flow naturally. Yeah.
Let's do our introductions. Kevin, please start, and then we'll have the others from our group do the introduce themselves.
Oh, I thought we were gonna go to Knowledge next.
As I haven't heard from Knowledge. Oh, Knowledge, you are unmuted. Let's have you speak, please.
Yeah, thank you, Raja. Hello, everyone. Can you hear me?
We can hear you fine. Yeah, we can hear you and see you.
Yeah, perfect. It's a great pleasure to be connecting with you again. Today we have a school from Harare, Irene Christian College, and Banani International School. I see Jane, who is the principal for Banani International School in Zambia. I see she is in the session.
Jane,
yeah. So for an intro, I am Knowledge Chikundi. founder and director of the Zimbabwe Science Fair and the Africa Science Baskets Festival. So I spend most of my time working with schools, promoting science, technology, engineering, and maths education. And so this year, I think we can say starting last year, we had Professor Raja speaking at the Africa Science Baskets Festival. It's a big event. It's an annual event where we get students from Africa and beyond, showcasing their research and science communication skills and talents. And so we had Raja speaking. And after that, we had 2 students from Harare making it into the SIP program run by the University of California, Santa Cruz. They had a wonderful experience. Like it transformed them. Right now, they are doing amazing things in their school. Maybe if time permits, I can play a video. I really enjoy one of their video productions as part of the SIP internship program. So maybe if time permits, I can play that video. And then we joined a session in September. Then we are now joining again this session. And the students really enjoy this. From September, they really enjoyed the session because after that session, I got feedback from most of the students who were in that session that they now enjoy, they are now more curious about astronomy and related science. So thank you, Raja, and your team for giving us this opportunity.
It's been your efforts really that has made all this possible. And when you connected last month, it was with Amanda and myself. I think we were in Hawaii, and you connected to our to the Keck telescope, and we were using the Deimos spectrograph to study the Triangulum galaxy. I think this was on the 13th of September when you connected.
Yes, 18.
And there were 3 schools that day, all from Harare, 3 different schools. Queen Elizabeth was one of the schools, but and we actually heard from the 2 girls who spent their summer working in SIP. And Kevin has been part of SIP for many years, been a mentor. So has Monica, including this past summer. So they're very familiar with SIP, and they've been involved in astronomy projects. And what Noku and Ru did was something at the intersection of astronomy and art, which was super interesting. It was their mentor was an athlete who's just been a tremendous mentor. We should hear from Jane. How are we doing in terms of the exposures? We are counting down. Okay, so you can see in this window here that do you see it says elapsed 296, 297, etc. So we have something like a little over 10 minutes, almost about 12 minutes to go, 11 to 12 minutes to go before this particular exposure finishes. So we have a little bit of dead time while the telescope is collecting light. That's what that readout is. It's telling you how much exposure time is left. And this is, of course, one of a few.
Yeah, this is two of 3 exposures. One,
okay.
The first one is the current image that's being displayed.
And this is a 1,000-second exposure, so that's that's a little over 16 minutes. It's overall it's going to be 3,000 seconds, so 50 minutes. So we would love to hear from you, Jane, if you have a.
I do. Thank you. Hello. Thank you. And hello from Banani School. I have a challenge because I have to have.
Oh, you've gone on mute.
I've muted me. There you go. I've unmuted me. My screen is flipped, so I'm having some challenges being able to do things like unmute. But we have here our grade 8 and 9 girls. Is that all at 8 and 9? And 10? So, and they're all,
Looks like Jane might have gone back on mute.
Yeah, I mean, I'm not, she's still on unmute, but we're not getting her sound. I can see that it's not muted, but we're not getting sound either.
Now it's muted again. Maybe it's a microphone issue.
Mhm. I have to give credit to one more person here. There's a
sorry, just quickly, sorry, we came back. we dropped, we dropped internet just for a moment, but we've reconnected. So yeah, so we have all our girls here. So if I actually do this, you may be able to see them all if I very carefully.
You're upside down.
We're upside down because we're flipped, but this is all our grades 8, 9, and 10 students.
Okay.
So they're here to, yeah, to learn about a little about astronomy and for us to start getting involved with the Science Busters again, because we have been in previous years and then COVID has sort of got in our way. But I think we're really excited about the opportunity to get back involved with Science Busters and to have this chance to see what real science is when it's happening at work in a real time. So thank you for inviting us.
You're most welcome, Jane. Which city are you located in?
We're near Lusaka. So
You're
we're,
near
yeah,
Lusaka. Okay, near the capital.
Yeah,
okay.
near Lusaka. Yes, yeah.
Okay.
And we are a girls' school, and our aim is to excite interest in the girls in science and technology, particularly. So that's our focus is always science and technology, and getting women involved in areas where they often are not well represented.
No, that is very well aligned with the mission of the science internship program that Rubarashi and Nokutenda were part of. In fact, that program traditionally has had 60% girls, 40% boys in the program. And it's sort of now that about 1,500 students have come through, and there's been many more girls in the program than boys. So we welcome that, and we would, we would love to partner with your school. This is, this is a program that runs over the summer. The way I think of this, if I can contextualize this just a little bit, we'll have many of these sessions. Tonight is the first, tonight is the first one in October, but we have 2 more of these nights in October. We have 3 nights in November and a total of 3 nights in December. So we have 8 more nights after this one. And we already have completed about a dozen nights in the months of August and September. So we'll be having these opportunities come up on a relatively regular basis, not just through December, but hopefully also in the months of January, February, March. We've asked for time on the telescope. There's a competitive process. We don't know exactly when those nights will be allocated to us, but once I know, one of the first people I inform is Knowledge and some of our other partners around the world. And so these will continue to happen. But the way I think of these is these are the scientific equivalent of going to the ocean, going to a beach, and dipping your toe in the water to see if the water temperature feels right. Okay, if it feels inviting or not. And that's really what these are. You get to see how science gets done. Today, it's real science. It's not polished, it's not packaged, it's not curated in any way. Kevin and Monica and Stephanie and Raphael and I are scientists. We are at various stages of our academic journey, but we are doing research. And you're seeing us do research in the same way that we would if you hadn't joined this Zoom call. We're not taking any special turns away from our actual process. And that's super important because we want this to be an authentic experience. But it's a passive experience for the students in the sense that apart from asking questions and listening to our explanations, it's not a doing, kind of exercise. It's really a passive exercise. But that's what dipping your toe in the water is. You're not making much effort except to dip your toe in the water. The water is whatever temperature it is. The next step in this journey is to actually wade into the water and learn the swim strokes so that you can then venture even deeper into that ocean and swim in a place where your feet can't touch the ground. So using this analogy, I would say that, you know, these telescope sessions are just dipping your toe in the water. Kevin and some of my other research students and I have been involved in something where we go and teach students how to write computer code in Python in the context of astronomy research. So it's not just learning how to code, but it's learning how to code in a way that is intimately linked to astronomy research. And I think of those as learning the swim strokes. Now you've learned how to do the crawl or the backstroke or the butterfly. And so those are the tools you need before you can venture deeper into the ocean. And the summer program that Rivarashi and Nokutenda participated in, those are really going into the deep part of the ocean where your feet can't touch the water. And there are dangers when you're doing open-ended research. There's danger of failure all the time, but it's not catastrophic failure. In that sense, the analogy with the ocean breaks down. It's not life-threateningly dangerous. It's dangerous in the sense of it's fraught with failure, and failure can be demoralizing if you're not prepared for it. Anyway, I just wanted to provide that context. I'm actually going to get up from my computer for a moment while the others talk, and I'm going to turn on the light in my living room because, you know, the light has timed out because it's you know, close to 1 o'clock here. Okay, Kevin, if you wanted to, you know, we still have another 3 minutes for this exposure. Should we go around and do more introductions now?
Sure. Yeah. Yeah, after that, happy to, because we still have another 1,000-second exposure after this. After introductions are done, we can walk through what the different screens are showing here and talk a little bit about the science that we're doing tonight and with this project. And yeah, just generally saying that we've been getting a broad range of questions and they've been great so far. So anything you're interested in, hopefully we can give you an answer. Kevin, I am a 5th-year PhD student at the University of California, Santa Cruz, where I predominantly work with Raja as one of my advisors, and then another faculty, Connie Ricosi, also in the department. And then I also work with a bunch of other collaborators who aren't necessarily at Santa Cruz. For example, Monica, who's leading this project. So I'm a PhD student. Most of my work involves using spectra of stars. So that's what we're looking at here and what we're collecting tonight. We're collecting spectra of stars, which is, you know, the amount of light at every color or every wavelength from a star. And so what I tend to do is I take the spectra of stars and try to analyze the features in those spectra to try to learn about the properties of the stars. This includes things like its temperature, its pressure or gravity on its surface, the amount of iron, the amount of other chemicals, its distance, its velocity. These are some of the things that we can learn from a star's spectrum. And so I take spectra of stars, mostly of stars in the outer regions of our galaxy, to try to learn about the history of our galaxy. Stars in the outer regions of our galaxy tend to be older and tell you a lot about the environment that our galaxy was formed in. And so by understanding the properties of stars and the environments that they were formed in, we can learn about kind of the early history of our galaxy, or how our galaxy has evolved over time. So those are some of the questions that I tend to think about. That's not exactly what we're doing in this project here, but this project again uses spectra of stars to try to learn about stars. And so that's very near and dear to the things that I study. And that's me. So I'll pass it over to maybe Monica next. If you're, yeah, okay.
Can you guys still hear me? I'm in a
Yes.
hotel with really sketchy internet. So
Yeah, we can hear you.
yeah. So I apologize, can't be on the video. But hello everyone. My name is Monica Saraisam. I'm an associate scientist at the Gemini Observatory in Hilo, Hawaii. So as Kevin just described, I've been working on this project with this team. So Kevin, Raja, and we've got two more undergraduate students, Stephanie and Rafael. I think we began this campaign like fall of 2019. So we've been gathering all these spectral data for variable stars in Andromeda for more than 3 years now to try to understand from their spectral signatures what's actually happening that's causing the variation that we see in these stars. So generally, my research, my more generic research area is tandem astronomy. I work with a lot of data which are gathered by astronomical sky surveys, which are like scanning the sky every night and sending us alerts on astronomical sources, which are varying in time. Then we use these bigger telescopes, like for example, to get spectral data for these interesting events and try to make sense of their physics. So I think I'm gonna pass on to either Stephanie or Rafa if you guys are still there.
Yeah, I can go next. So I'm Stephanie, and I'm a 4th year undergraduate at UC Santa Cruz. And I've been working on this project as like a research assistant for 2 years. And so basically I just plan out these observation nights and run the data reductions. And yeah, just take care of the science and work with the group to make proposals. And it's been really fun.
Yeah, I guess I should also introduce myself. I'm Rafael. I am I guess I finished my undergrad already. I just graduated in July, but I've been working with this research group the past 3 years, and I mostly did, I did a lot of the early stuff, getting the project started. So I did a lot of the early spectroscopy and like analyzing actual spectral data and getting classifications going for the early unclassified stars. And I've also more recently just gotten to the writing portion and various things like that. And yeah, I plan on sticking around with the project for as long as I can and sticking with astro research.
Yeah, thanks everyone. I don't know if there's anyone we have left off, but I'm happy to give a tour of the different screens that we're seeing here and talk about the data that we're collecting. At the same time, introduce Dan in the 120 ROR Zoom room you'll see there.
Hello, everybody.
Yes.
Hey, Dan.
So yeah, Dan is sitting in a room, 10, 20 feet from the telescope that we're operating tonight. And so Dan is our telescope operator who's basically driving everything for us. He's making sure the telescope's taken care of and safe and pointing it where we want it to be and based for us. Anything else you want to add to that, Dan?
I don't know as I've got anything interesting to say. Unlike the majority of the team, I'm actually a mechanical engineer rather than a physicist. So all that does is prove that it takes a variety of disciplines to do science.
Absolutely. Yeah. Getting a telescope working takes a team of mechanical engineers, electrical engineers, software developers, the astronomers, the physicists, everyone's involved, the material scientists. So even if if your passions are space, you don't necessarily have to be an astronomer to contribute to the science goals. Okay, so I'm going to walk through some of the things that we're seeing here and maybe talk a little bit about the science that we're doing tonight and for this project. But on each one of these screens, there's a few different pieces of information that I'll draw your eyes to. The first screen that we're looking at here is what I'll call the blue screen because we're looking at blue data. And then the second screen is the red screen because we're looking at red data. And then this fourth screen is like our guider screen. So I'll go back to the blue screen here. And what we're doing is we're collecting spectra of these stars. So what happens is the light from the star enters the telescope, and then we basically feed it through a prism so that it breaks it up into a rainbow of light. And then because of how the telescope is designed, we take half of the light and put it in what we call one arm, and then half of the light goes in the other arm. So the the shorter wavelengths goes down the blue arm, and the longer wavelengths, the red wavelengths, goes down the red arm. And so this is the blue data, and the spread out light from the stars. And I'm going to pull up an example of a brighter star because that'll make it a little bit clearer. We're looking at some pretty faint things right now. Perfect. Pull the same one up here. Oh, no, that wasn't the right one. That's okay. I'll come back and find it in a second. Okay, so we take the light from the star and then we break it up into the two pieces, the red piece and the blue piece, and then all of the spectrum of light, the rainbow of light that's blue, ends up on the LED here. The same piece of technology that's in your camera if you have one of those, or your phone camera. And what we're interested in is the amount of light that wavelength or at each pixel along here. So if I take a slice along the rows here in this bright region that is the star's light that I can get a graph that looks like this, or a plot that looks like this. And this is almost it's basically the spectrum of the star. It's telling you that there's twice as much light at this pixel as there is at pixel from the star. And this is the blue light from this star. And I can do the same thing for the red data. If I find the right matching observation, let me just check my log so I know which one I should pull up. 57, wasn't even close. Okay, so this should be the same star. Sorry, my computer's being a little bit slow right now. There we go. Okay, so there we go. That the blue data goes from left to right, and the red data goes from top to bottom. And so if you're familiar with wavelengths, the left side here is our bluest wavelength. And the right side here is kind of our intermediate wavelength, where we cross between the two arms, the blue data and the red data. And then it picks up at the top here and then goes to longer wave at the end. The exact wavelengths that we're measuring here go from, I believe, 300 nanometers, which is like in the near ultraviolet, which your eyes can't pick up to 800 nanometers, which is in the near infrared, which again, your eyes can't see. So we basically cover the full wavelength range that your eye is able to see. And so if you were looking at this with your eye, this would appear as pretty blue light, and this would appear as pretty red light. Okay, so continuing on with our explanation here, we can see this, and this is the thing that we're actually interested in. And you can see a general shape here, this nice gentle curve with a few very strong dips in it. And it's mostly these dips that we're interested in, because these dips tell us about the structure of the star, it tells us about the properties of the star, it tells us about the chemical composition of the star, it tells us how quickly the star is moving towards us or away from us. Yeah, by looking at these strong features here, or any of these features, we're able to learn about the properties of the star. So if I zoom in on one of these features, you see this, this big strong dip is a elemental feature produced by hydrogen in the atmosphere of the star. So you have your star, and just like Earth, the star has an outer kind of gaseous envelope around it. And as light leaves the center of the star, it passes through the atmosphere of the star, and then it goes through space, and then it reaches our telescope. And as it passes through the atmosphere of the star, it interacts with the chemical elements that are in the atmosphere of the star, and those produce these signatures that we see here. So I know, based on occurs in this star spectrum, that this big dip right here is because of hydrogen. So this feature here is because there's a lot of hydrogen in the atmosphere of this star and in all stars. And some of the things that we can do is we can measure the shape of this line, how deep it is, how wide it is. And that tells us about the temperature and the pressure of the star, as well as how much hydrogen there is in the atmosphere of this star. And things we can do is, because we're able to interact with the chemicals in a lab on Earth, I'm able to, in a lab, I'm able to measure where I expect this feature to occur, what wavelength I expect this feature to occur at. And if I measure this feature occurring at a different wavelength, this is because of Doppler shifting of light. And maybe you've talked about this in some of your classes, but if something is moving towards me, light will be blue shifted. If something is moving away from me, it will be red shifted. And basically the offset of where this feature occurs versus where I think it should occur tells me exactly how fast that star is either moving towards me or away from me. And so these are some of the things that we can extract from a spectrum to learn about the stars. So unless someone else wants to chime in and remind me of something that I've forgotten, most of kind of a description of the measurements that we're making here. And then this final here is it's more like a classical picture of the sky where we're seeing basically the stars in the region of the sky that we're looking at. There's this vertical bar here that is there's a piece of metal here, and there's a gap in the piece of metal that is allowing the light to enter the telescope. And so that's basically what we're looking at here. We use this to help get the telescope aligned on the target that we're interested in, and then making sure that its light is going to enter the telescope in the way that we want it to. So I think that's my overview of the things that we're looking at here. Raja, is there anything you wanted to add?
Kevin, this was terrific. I wanted to add some small factoids. One of them is the typical star we're taking a spectrum of, I would say, is something like 15th magnitude or fainter. And I just want to put that into context. If you go out to a very dark site away from city lights where the atmosphere is clear and there's no cloud cover or dust blocking the light of stars, The faintest stars you can see are, we use a magnitude system. They're fifth magnitude. The brightest stars you can see are 0th magnitude. The faintest stars you can see are fifth magnitude, and they're about a factor of 100. The faintest stars we can see are about 100 times fainter than the brightest stars we can see. Now, mind you, planets, and of course, something like the moon and of course the sun are much brighter than that. But the brightest stars, non-planets, brightest stars we can see are about 0th magnitude, and the faintest stars we can see with the unaided eye, without binoculars, without telescopes, are fifth magnitude. The stars we are looking at are 15th magnitude and fainter, some are as faint as 19th magnitude, but the 15th magnitude star is 10 magnitudes fainter than the faintest star the eye can see. It's an inverted system where the bigger the number is, the fainter the star is. It's also a logarithmic system. And it's not a straight logarithmic system. You take the decimal log of the brightness and you multiply it by the number -2.5. So it's an inverted logarithmic system. Now, that sounds complicated mathematically, but here's a simple way to look at it. Every 5 magnitudes is a factor of 100. So I remember I said the 0th magnitude stars are the brightest stars we can see. 5th magnitude stars are 100 times fainter than the brightest stars we can see. A 10th magnitude star is 100 times fainter than the faintest stars we can see. And a 15th magnitude star is not 100, but 100 multiplied by 100. So 10,000 times fainter than the faintest stars we can see. So the stars we are taking spectra of here, not the one whose spectrum Kevin's showing, that came from Shukanya, I assume.
Yeah.
That one is actually only a few times fainter than the faintest thing, the 2 or 3 times fainter than the faintest thing the human eye can see. But the majority of the objects we're taking spectra of tonight are something like 10,000 to 30,000 times fainter than the human eye can see. So I wanted to point that out. The second remarkable thing, sorry, I can pause here if that's one fact, right? I wanted to put out here just how faint this light is. And of course, our eyeball is only.
Sorry, Raja, I'm gonna jump in because we're gonna move to a new target.
Okay, so I'll come back in.
Okay, I'm sending new coordinates to POCO and we are ready to move.
Okay, we're on the way, 2355.
And I have a, yeah, I'm just gonna calculate an average one again. I have a PA of 112.
112.
And this will be a 17.9 magnitude star. There isn't anything nearby it, so hopefully we don't need to find a chart.
Yes, I overshoot. For those of you watching at home, you can see the sky rotate as I change the angle of the instrument.
Yeah, so now we're basically looking at kind of a webcam view of the sky, and each one of these bright spots here are stars. So we're trying to locate our next target.
So based on what I'm seeing in the historical record, we've got these 2 items pointing to this item, which should be our target.
Yeah, I agree with that. I just need to rotate my head 30 degrees. Yeah.
Yeah. Didn't know you needed to do stretches before you.
It's good for my health.
Yes.
Okay, so we've changed print where now you can see again the actual gap in the piece of metal of the telescope that lets in the light of the thing we're interested in. And so the thing we're interested in is this bright spot here, which is moving.
You keep breaking up a little bit there.
Kevin, unfortunate.
Your net might be a little unstable.
Yeah.
And you're planning to use a 2 arc-second slit?
Yes. Can I open it back up?
Give me a second here. Wait for the telescope to decide which direction it's going to lean.
Sure.
Get back in there. Okay, you may set your slit. And for the home audience, what we're about to do is actually go find something bright in the nearby sky that we can guide on. Because when he opens that slit up, the light from the star we're actually interested in disappears. And so we have to use something else to make sure that it stays put if the wind blows the telescope. And so you may begin.
Okay. Perfect. Okay. We're going to be here for 30 minutes.
How bright is the subject, Kevin?
17.9.
Okay, nearly 18.
Mm-hmm.
So that's 3 magnitudes. What is 3 magnitudes? Can I do this in my head? Not quite. I don't know. Actually, I can do 3 magnitudes in my head. 3 magnitudes is a factor of 16. It's very convenient because 2 magnitudes is a factor of 2 is 0.75. So square that. Factor of 4 is 1.5. And you square that, and you get factor of 16 is 3 magnitudes. So it's
too late to be doing mental math.
I agree. So 16 multiplied by 10,000, so 160,000 times fainter than the faintest star the eye can see. I wanted to say one more thing about these stars. They are part of not our home galaxy, the Milky Way, but they're part of the closest galaxy that is bigger than our home galaxy. So imagine, you look out of your window at night. There might be other homes. Your neighbors may have homes, and if you can pick out the neighbor whose home is the nearest neighbor whose home is bigger than yours, that's what we're looking at. The Andromeda galaxy is the nearest neighboring galaxy that is actually slightly bigger than our own Milky Way galaxy. It's 2.5 million light years away. That means light, even though light travels very fast, it travels around the world 7 times in 1 second, travels from the moon to the earth in 1 second. It takes 500 seconds to travel from the sun to the earth. It takes about a day to travel across the solar system. It takes 4 years to travel from the sun to the next nearest star. But it takes about 100,000 years to travel across the central part of the Milky Way, about 5 times that, 500,000 years, so 500,000 years to travel across the entire Milky Way galaxy. But it takes 2.5 million years to travel from the Andromeda galaxy to us. 2.5 million. So human beings, as we know them, were not around when light left the galaxy to start traveling towards us. I mean, human beings of a different kind, are the kind of creatures we evolved from. They were on Earth, but not, the Earth was a very different place, not geologically, because geological age-wise, 2.5 million years is not that long, but from a standpoint of life on Earth, in terms of the species we enjoy around now, the Earth was quite a different place. Mind you, the dinosaurs, of course, lived even a longer time ago. But it's quite remarkable that, we have this telescope. It's 3 meters in diameter. It's a piece of glass that's 3 meters in diameter. But we are not only collecting light from a star that's where the light has been traveling for 2.5 million years, but we are not just collecting that light, we're splitting it up into sort of the thousands of colors that make up, white light, and measuring what chemical composition it has, how fast it's moving, what its temperature is, what its pressure and gravity are. So it's quite remarkable. And it's really the power of physics. People say that picture is worth 1,000 words. A picture is worth 1,000 words. A spectrum is worth 1,000 pictures. So a spectrum is worth 1,000,000 words, I guess. A spectrum contains a lot of physics information about stars. And that's one of the reasons we have this project here, is we're trying to understand the physical properties of the stars whose light is seen to vary in time. We're particularly focused on stars whose light is, whose brightness is changing with time. Okay, so I wanted to add that. That's a lot.
I just wanted to jump in, and because I wanted to look this up. The first homonyms, so like the first things you would recognize as almost human, are 2 million years ago. So
oh wow, okay.
Yeah, this light is even older than anything we would recognize as human.
Wow, so that's crazy. And how long have Homo sapiens been on Earth?
Oh, I think it's 300,000 years.
So well less, much less than that. So even the light from the edge of our own galaxy, well, actually, the light from the edge of our own galaxy takes about that long to reach us. You know, that's 300. Yeah, that would be about 100 kiloparsecs. Right, 100 kiloparsecs would be 300,000 light years, and so yeah, even light from the outer edges of our galaxy. Yuting has found stars that are 300 kiloparsecs from us. Oof. So 330 is his most distant star. So those have been traveling, yeah, pretty much 3 times as long as Homo sapiens have been on the Earth. It's quite remarkable. I mean, it is. I mean, the light started traveling to us before the species that built the telescope to collect the light was even around. So we sort of let's sort of take a moment to think about that. It's really really remarkable. I think we get numbed by this as astronomers. We come across these numbers all the time. Literally, they're numbers. They numb us into forgetting how remarkable this is. That's what numbers do. Maybe that's how they got their name. But I just wanted to say that. I just wanted to say how remarkable it is. And by joining our call today from halfway around the world, almost exactly halfway around the world, you are really reminding us of how privileged we are to study these things, and how remarkable it is that we can point to a piece of glass and metal we call a telescope and collect information about the universe we live in. Okay.
Yeah, absolutely. I echo those statements. So to make things a little bit more concrete, or maybe a little bit less philosophical, the things that we're actually measuring tonight and a part of this program are stars who change. That's broadly the goal of this project. It's called the Salvation Project, or Salvation Survey. It stands for Spectroscopic Analysis of Luminous Variables and Transients in Our Neighbor. Did I get that right?
Yes, that's exactly right.
Perfect. It's a long acronym, Salvation. So anyway, the goal of this project is to study stars in the direction of Andromeda, mostly, and try to get spectra of stars who are, so that's the variable stars, variable meaning their light changes over time, and transients, which are a different type of star that change over time in that they, they're basically, if you're looking at another galaxy, it just looks like a normal galaxy, and then all of a sudden it starts brightening like crazy, and then it goes away over the course of a month, like supernova, which you maybe have heard of. These big explosions that from a single star can suddenly outshine an entire galaxy. So these are the types of objects that we're collecting spectra for. And in particular, what we're doing is we're collecting their spectra at lots of different times. So if we're studying variable stars, we'll measure many times over the course of months to see how things change over that time. when it comes to the transients, they tend to change relatively quickly, but we're doing the same thing with those, where we're seeing how things change on a day-to-day basis, or on a month-to-month basis, or on a 3-month basis, or a year basis in some cases. And doing this is because there's lots of uncertainty about stars. There's lots of things we don't know. And in particular, these types of stars who change over time, are not nearly as well understood as stars like our sun, who are, who have a relatively stable life. If you measure the light of the sun, or how bright the sun is, that doesn't change much over time, or even over the course of millions of years. But if we're talking about some of these variable stars, their brightness can fluctuate pretty substantially over the course of days or weeks or months. And so astronomers don't necessarily know all of the physics that's going on in these stars to cause these changes in brightness. And so what we're hoping to do, measuring their spectra over time, we can use those spectra to measure things like their surface temperatures and their gravities and their chemical properties over the periods of their pulsation to help us understand the physics that's going on in these stars, and then hopefully understand help us understand better just stars in general. And so we're looking at stars in Andromeda, but it's just a good set of stars to be looking at, but it's telling us about stars in general. So that's this project. Okay, this one's looking good. Yeah, and so I think with that, I'm happy to open it up to questions more generally about anything we're working on here, or just space news or stuff in general. We were answering questions about pulsars and dark matter and dark energy earlier, but happy to answer questions about what we're doing here, how the observing on a telescope works.
This is a great time for us to take questions, as you said, Kevin. This is anyone from either school. If you're Vanani is one of the schools, Vanani, and the other school is Irene Christian College. If you have any questions at all for us, it could be related to what you've heard. It could be anything really.
Morning.
Good morning.
My name is Adrian Kabadi from Irene Christian College.
Hi.
I just wanted to ask.
Sorry,
I just wanted to ask whether there's a telescope stronger than the cast spectrograph at the current time.
Yes, there are. There are many telescopes right now that are more that have bigger area to collect more light per unit time. The power of a telescope, one of the things that determines the power of the telescope, the main thing that determines the power of the telescope is how much light it can collect per unit time. And that is really related to the area of silvered surface, area of the mirror. So the area of the telescope that the cast spectrograph is connected to is, well, the diameter of the mirror is 3 meters, 120 inches. We tend to use, both metric units and British system units, but 3 meters. And so that's the telescope we're using tonight. We will occasionally, our group occasionally uses the Keck telescope, which has an effective diameter of 10 meters, not 3. And, since the area of a circle is proportional to the square of its diameter, the Keck telescope is more than 10 times the collecting area of the Lick telescope. So I don't know if that answers your question. There are telescopes that are 5 meters in diameter, 6.5 meters in diameter. There are telescopes that are 4 meters in diameter. There are, many telescopes now that are somewhat more powerful or comparably powerful to the telescope we are using tonight.
That answers my question. Thank you very much.
Sure. The CAS spectrograph, though, which is the instrument that takes the focus light and disperses it into the colors of the rainbow, that is one of the best spectrographs I have ever used in my 36 years as an astronomer. I've used many spectrographs, and the CAS spectrograph is really fantastic in terms of how well designed it is and how, there are very few instrumental artifacts that it produces, and it really provides a very clean view of the universe. Adrian, which grade are you in?
I'm in grade 11.
Ah, okay. Okay.
Yes.
So you'll be taking the A levels next year?
Yes, I will.
Okay, got it. Thank you for your question. Other questions, please? That was, that was a very good question. Kevin has stepped away for a few minutes, but please ask your question. Please go ahead. Yeah.
Hi, my name is Leleti Mzondori, and I wanted to ask, what is the expansion in the universe accelerating?
Oh, that's a very good question. We were talking earlier in the night about this mysterious substance that we don't understand called dark energy that is pushing galaxies away from each other, causing the expansion of the universe to get ever faster with time. I think it's fair to say that we don't understand the details of dark energy, which is the entity that is causing this outward pressure. We don't understand the full details of it. This is what many scientists are spending their careers studying. I was also saying to the group that yesterday and today I've been in conversations, phone and email conversations with two people, two astronomers. Their names are Adam Rees and Brian Schmidt. And the reason I mention them is because they received the Nobel Prize in physics for the discovery of dark energy and the ever accelerating expansion of the universe. So it's interesting that you're asking about the expansion, because I was just literally talking on the phone on Monday with one of the people who got the Nobel Prize for this discovery. He's a longtime friend and acquaintance, and I was exchanging email with him and another one of his. There are three people who got the Nobel Prize together for this discovery, and they would be the ones to tell you, even though they discovered that dark energy is a thing that's pushing galaxies apart, they would be the first ones to tell you that we don't understand its detailed nature yet. I say yet because there'll come a time when we will have a better understanding of it, I'm sure. That's how science progresses. Does that help answer your question?
Yes, it does. Thank you.
Thank you. It's a great question. Thanks. You know, when I was in school like you, many years ago, many years ago. I remember that, most days we would go to school, we would go to class, we would study our subjects. It was the same teacher who was teaching a particular subject. If it was history, then it would be our history teacher. Geography would be the geography teacher. There was nothing new from day to day. It would be the same person. If it was a particular subject, it was the same person who we'd seen teach that subject, weeks ago, months ago, years ago. And one day we had a visitor to our school who was famous because she was known as the human computer. And she was remarkable in her mental math. You could tell her that I am 17 years old and my birthday is the 13th of October. And without thinking about it for more than a second, she would tell you were born on such and such day of the week. She would be able to do that in her head. She was very good at mental math, and she would take leap years and all of those things into account in her head in a matter of a second. And that so inspired me that somebody could have that kind of brain power, that kind of mental math power, really inspired me as a child.
Good morning. My name is
Morning.
Dunsan Charukwa. And I would like to know that in terms of composition, how are different types of stars different from each other?
That's a great question. And if others want to jump in, you should please. Stephanie, Raphael, Monica, if you want to jump in, please do. I will start the answer, but I'm hoping they will chime in. The main thing that sets one star apart from another, the main thing is how massive it is. So the more massive a star, the more vigorously it undergoes fusion reactions, the more intense its own gravity, its self-gravity, and the higher its temperature. And massive stars tend to burn very hot. They tend to burn very bright, and they live for a very short time compared to a star like the sun. And the reverse is true. If a star is very low mass, you can have stars that are 1/10, actually even less than 1/10, 8 parts in 100 of the mass of the sun is the other sort of mass of the lowest mass stars. And those are just the opposite. They don't have very strong gravity. They burn very slowly compared to the sun. They don't put out as much light as the sun, much less light. Their temperature is much lower than the surface temperature. And if you compare surface temperature of sun to such stars, much lower. Interior temperature is also much lower than the interior temperature of the sun. And so mass is the main thing that sets one star apart from another. Other things are important too, like what chemical composition a star starts out with is also important. But chemical composition doesn't vary that greatly from star to star. Mass varies by huge amounts. The lowest mass stars are, like I say, less than 1/10 the mass of the sun. The highest mass stars are 100 times the mass of the sun. So there's a factor of 1,000 in between lowest mass and highest mass stars. Chemical composition, most of the star is hydrogen and helium. Something like 98% of a star is hydrogen plus helium. Hydrogen is about 75% and helium is about 23%. So it's really in that remaining 2%, whether it's 2% or 1% or 0.2%, are the rest of the elements in the periodic table. So you can see that chemistry-wise, stars don't vary that much in chemical composition. Other things that matter are what phase in a star's lifetime it's in, whether it's a main sequence star or red giant star, exactly how it's, where and how it's undergoing its nuclear fusion reactions will also determine the properties of a star. Does that answer your question?
Yes, it does. Thank you.
Raj, that there's also a question of when the star formed.
That's right, the age
The
of the
very
star.
small, very old stars have less other material in them than stars formed recently, which have collected dust from previous supernovae, and so have more stuff in them besides hydrogen and helium just from the get.
All
I don't
right,
know if that or not.
Jane. Jane, are you? One second.
We are getting a lot of noise from, yeah, from that connection, from Jane, from your connection. A lot of background noise. These are great questions, but there are other questions that we can take.
Yeah.
My name is Bradley. I have a question.
Please go ahead.
Is there a nebula in the Milky Way, and how far is it away from ours, or from our solar system?
There are many nebulae in the Milky Way, many nebulae. One of the closest ones is the one in Taurus. The Orion Nebula is not that far away, in the sword of Orion the Hunter. The Orion Nebula is also quite spectacular. There are many nebulae around us. There's something called the Ring Nebula. There's something called the Hourglass Nebula, the Cat's Eye Nebula. There are many nebulae. Some of them are associated with individual stars. That is the death or late stages of life of individual stars, where they're ejecting material from them. But some of them, most of the really spectacular ones are associated with the birth of stars. That is, they are like stellar nurseries where new stars are being born. Orion and Taurus are good examples of nebulae where stars are being born. Our Kevin has got some lovely pictures there. Look at that. Wow. These are pictures of nebulae.
These are probably some of the most beautiful structures in the universe, or at least to me anyway.
Lovely colors. And
Yeah.
the one in the upper left is called the Horsehead Nebula. It's in the Orion Nebula. You can see the shape of a horse's head if you click on that one.
But as Raja was saying, these are like stellar nurseries. So this is where a star has died. It has given up its all of its gas and dust. It's exploded out. It's enriched the environment around it with new chemicals that it made as it was dying. And then in puffing out all this gas, eventually that gas recollects and starts forming new generations of stars. So here you're looking at all the exploded out material from an old star that died very cataclysmically. And then new stars are being formed from the material that was ejected. So that's why these are called stellar nurseries, because you'll have lots of young stars being born in this gassy, cloudy, dusty mess that you see here. Yeah, these are beautiful. I think some of the most beautiful structures in the universe.
Okay, hello, my name is Dari Cherry, and I would like to ask a question.
Please go ahead.
Okay, so why are some orbits of planets elliptical?
Why are some of the orbits of planets elliptical? It has to do with quantities. There are two quantities that are important when one object orbits around another. Whether it's a planet orbiting a star or a moon orbiting a planet, there are two quantities that are important. One is called energy. One quantity is energy. The other is called angular momentum. And these two quantities are determine the shape and radius of a planet's orbit. The shape, meaning how elliptical or circular it is, and the radius, meaning how far away from the central object it is as it orbits. In general, the higher the energy, or the less negative the energy, the larger the radius of the orbit, if all else is equal. For a given central object, the larger the radius, the less negative the energy. And angular momentum, on the other hand, is related to how circular or elliptical the orbit is. And coming back to the conditions, it really, a good way to think of it is there are multiple ways in which something can respond to the gravity of something else, right? If I take a ball in my hand and I drop it, if I just drop it, if I just let go of the ball, it falls directly towards the earth. It falls in a straight line. And in other words, it forms a highly elliptical orbit, almost a perfectly squashed ellipse. If, on the other hand, I throw the ball horizontally, it follows a curved path. And if I throw it hard enough, if I throw it harder and harder horizontally, it travels further and further with less and less curvature. And if you could throw a ball hard enough, it would go into a circular orbit around the Earth. And if you could, and then if you start increasing the velocity beyond that, it goes into more and more elliptical orbit when you do that. So it really has to do with the energy and angular momentum of the particle. I don't know if that answers your question, but in general, orbits are elliptical. Almost all orbits are elliptical. No orbit is a perfect circle. They can be very close to circular, but they tend to be elliptical. The moon's orbit around the Earth is an ellipse. The Earth's orbit around the sun is an ellipse. Pluto's orbit is a very extreme ellipse as it goes around the sun. But elliptical orbits are very common out there. This is something.
Just 1 second here before the next questions. We've started our readout on red. I've sent new coordinates to Coco, and we are good to move.
Okay.
And I have a PA of 100.
100. And we started our slew at 0:30.
And Kevin is
Hello,
narrowing the
sir.
slit. Sorry, just a moment, please. Just give us 1 moment while we get the new exposure started. Kevin is getting that started. We'll take more questions.
And Dan, I've sent you a finder chart if it's necessary. It's I believe like an 18.8 magnitude star.
That might be. I have it. Okay.
Hello, sir.
One second. If we could just wait on the questions until we've started our next exposure, that'd be helpful.
Yeah. We should be able, just give us less than a minute. We should be able to start this.
Yeah, when I say you may begin, then we're ready for questions again. Didn't we do this last week?
I don't think so, because I didn't have a finder chart. Do you mean on the 23rd?
No, I just remember this field from, or a very similar field from something else. Let's see. Looks like we went direct.
Perfect.
Which says that seeing is very good today. I'd love to give a number, but I would have to slew away for a moment. That'd be a waste.
Let's not waste the good seeing.
Right. And again, you said you wanted a PA of 100.
Yeah.
You may take your start.
Okay.
And you may begin. All right, I think we're ready for questions again.
Yes. Yeah. Yeah, Irene, Christian College, if you'd like to keep asking questions, we're ready for more questions now. Sorry for having to cut you off there.
Hello, sir.
Hello.
My name is Takunda Marongo, and I wanted to ask that if a black hole and a star makes contact, what would happen?
That's a great question. I think this is a relatively active research that people are still trying to answer all of the details of this, but there are some beautiful simulations that people have been making recently of stars falling into black holes and being eaten by black holes. But going back to the last question, the two things that matter when two objects are colliding with each other are energy and angular momentum. And this kind of sets how close they'll get to each other. And because of the conservations of energy and angular momentum, you get these really interesting things happening. So you can imagine a star passing close by a black hole. It'll get very close to the black hole, but because of the conservation of angular momentum, the part of the star that's close to the black hole might get ripped off and fall into the black hole. And then the other part, because of the conservation of angular momentum, will spray out in this big long arch so that angular momentum is conserved. So when a star basically falls into a black hole, the star will get ripped apart and spread out into a big long stream. And part of it will potentially fall into the black hole or end up orbiting the black hole. And it can orbit the black hole really fast, and this can produce really energetic light that we can see because it's orbiting so quickly. Yeah, that's it, it's a very violent process. So if you are interested, you should look up some of these simulations of stars colliding with black holes. They're beautiful. Roger, do you have anything to add?
They're called tidal disruption events.
Yes.
The term tide, T-I-D-E, means differential gravity, where the near end of the star is being pulled harder than the far end. So one of the students who is, I guess, 2 years your junior, Vivian, at UC Santa Cruz. So she's starting her third year, right? Is that right, Kevin?
Yeah, I think so.
Miranda's 1 year your junior and Vivian's 2 years your junior. She's starting her third year. She's been working with Piero Madao and me. Piero is one of my faculty colleagues at UC Santa Cruz. And she's looking for these sorts of TDEs, tidal disruption events, caused by a special type of black hole called intermediate mass black holes. They're much more massive than the sun. They're between 100 to 10,000 times more massive than the sun. We don't know if intermediate mass black holes, whether they're common or very uncommon. We are trying to find that out. And the way we're trying to find that out is if they do exist, they should be able to disrupt stars. They should live in star clusters, and they should be able to disrupt stars from time to time. That's what we're looking for in some time domain data sets. These are great questions. Were they? Please keep asking questions. Were there other questions you have?
Yeah, thank you, sir.
Thank you.
Hello, sir.
Hey.
I have a question. How far can scientists capture, as in, can we go outside the Milky Way, and how far can we go?
I missed the first part of your question. How far can you capture light from?
No, how far can astronomers capture outside the Milky Way?
Capture light, you mean? Capture information or what? That's a very good question. The furthest light that astronomers have seen has been traveling for over 13 billion years. So this is the light that we see from the Big Bang, from the afterglow from the Big Bang. You know, when you, it's like when you light a fire and you extinguish the fire, the embers of the fire remain warm for a little while. The universe was very hot shortly after the Big Bang, and it's gradually, very gradually cooling down. Over 14 billion years, it's been cooling down, 13.7 billion years, it's been cooling down. So that glow that we can see from the Big Bang is the furthest information that has been captured by astronomers. Does that answer your question?
Yes, sir. Thank you.
Thank you. It's very exciting to study the afterglow from the Big Bang. You know, shortly after I completed my PhD, that was a direction my studies were going to take me. I was going to study the afterglow from the Big Bang, but then some things happened and I started a different project instead of that. I mean, I started that project and then a different project came along that took all of my time and attention, and I never ended up studying the afterglow from the Big Bang. Oh, you're going to show a movie. Wonderful.
Yes. Yeah, I was gonna. So going back to the last question, because I had a simulation in mind, and I thought it was Santa Cruz related. James, I don't know how to pronounce it.
Gyoshan. Yeah, Gyoshan.
Yeah. Santa Cruz connection. So that's fun. So this is a simulation of a star passing by a black hole. So you're going to see a star moving, and you won't see the black hole, but you'll see what happens to the star over time. So it'll be in the upper left. So there you go. And it happens quickly, but the star gets completely ripped to shreds. And part of it gets spread out, but part of it continues to orbit around the black hole. And you get this kind of funneling around the black hole. So this is the tidal disruption event that we were talking about. And these streams will stretch very large scales. Yeah, so there's lots of cool information about the merger, but I'll go back here. So you can see, if I go back just a step, let's see, pause it at the right time. So the star is right here, and the black hole is this little, maybe it's hard to see, but there's a little red dot here. So the star has some actual size, and so some of it is closer to the black hole than other parts of it. And basically half of it gets, or it gets ripped in half, and half falls in, and half gets ejected. So this is all the material of the star getting spread out. So the star is completely shredded. Yeah, so some very cool simulations.
So one thing you can see from simulations like these is astronomers don't just use telescopes as the only instruments to study astrophysics of the universe. They also use computers. Computers can do today's computers can do really powerful, quick calculations that would have been unheard of 10 years ago.
Yeah, and I'll add that it's kind of really the marriage of people at the telescopes and people doing the simulations that really progress astronomy. It's, someone comes up with a theory about the universe and someone builds it into a simulation, and then they can turn around and tell the observers like us, hey, I'm predicting that there should be this interesting thing out in the universe. Try and go find it for me. Or the other way is true, where an astronomer or an observer will say, I found this really weird thing out in the universe. And then the people on the simulation side will try to reproduce that in the simulations. And if you're able to perfectly describe what we see in the universe, then the physics that you put into your simulation are probably close to the truth. So it's kind of this back and forth ping pong game that allows us to advance astronomy and our understanding of the universe.
Hello there. My name is Ryan.
Hi.
Yeah, I wanted to ask what type of celestial object would the sun be when it dies? Essentially.
There are, what type of celestial object will the sun be when it dies? Did I hear that correctly?
Yeah.
Okay. So
Yeah.
the sun is not expected to explode, but is expected to get much bigger, but not in an explosive way. In a controlled way, it'll get bigger. It'll turn into a red giant, and then it'll shed some of its outer layers, and its death will be in the form of a star, of a kind of object. It won't be a star anymore, but it'll be a dead star, something called a white dwarf. It's a type of star that is very hot on the surface, but not very big. It'll be about the size of the Earth. The sun right now is much bigger than the Earth. The sun's radius is 1 million kilometers. The Earth's radius is only 6,500 kilometers, 6,400 kilometers. So it'll become much smaller because the outer layers will be lost and the central part will shrink. But it'll shrink to about the size of the Earth, and it'll cool down gradually over time. Over billions of years, it'll keep cooling, and it'll die as something called a white dwarf. That's the end state of the sun. Now we can see other white dwarfs right now, other stars that have died as white and become white dwarfs. So we can get a preview of what our sun is going to look like by studying those objects.
And our understanding is that it'll be mostly made up of carbon and oxygen. So that's something that's interesting. And these things are not the most dense objects in the universe, because obviously there's neutron stars and black holes, but they're some of the most dense objects in the universe. And I believe something like a tablespoon of white dwarf would be as massive as a mountain on Earth.
Wow.
Yeah. So they're a very dense object.
What is his name, by the way? What is his name?
Another little fun fact about when it's reaching the end of its life, it'll probably like hiccup a bit as it's trying to like survive near the end, and it'll get out to like about the Kuiper belt once it's like at its full girth since a red giant. But yeah, that'll take a very, very long time to actually get to that phase.
Hello.
Hello.
Hi, I'm Nadia, and I wanted to ask, how do astronomers calculate the distance between the Earth and stars that are out there?
That is an excellent question.
Fantastic, yeah.
So a method called parallax is used, and a good way to think of parallax is this. If you imagine your two eyes to be the different locations of the Earth as it goes around the sun. Imagine your nose to be the bridge of your nose to be the sun, the location of the sun. Imagine your left eye and your right eye to be the locations of the Earth as it goes around the sun. Okay. Now imagine you have a star that's quite nearby. So if you hold your finger out in front of your face, that your finger is a nearby star. Your two eyes, remember, are the locations of the Earth 6 months apart when they're on opposite sides of the sun. If you close one eye, you'll see that your finger, you don't move your finger, but if you close one eye, you'll see that your finger is, let's say, against a certain door on the wall. But if you close the other eye without moving your finger, you'll see that the same, even though you haven't moved your finger, it looks like the finger is projected against a different point on the same wall. So it looks like if you think of the wall as very distant stars, a nearby star will be projected onto one set of distant stars at one time of the year, but 6 months later, when the Earth is moved to the other side of the sun, it will be projected against a different set of stars. And the bigger that change, the more nearby that star. If you take your finger further and further away from your nose and you repeat this experiment of closing one eye first and then the other eye without moving your finger, you'll notice that the relative position of the star of your finger doesn't change as much if the finger is very far away from your head. If you bring it very close to your face, when you close to the bridge of your nose, you'll see there's a big swing. So this method of parallax is used to measure distances of stars.
Thank you.
I'll put the word parallax in the chat, so you can also do a Google search on parallax. Using parallax is used to measure distances to stars.
The other thing that's kind of interesting is that we use a lot of different techniques at different scales of the universe to measure distances. So parallax gives you distances to nearby stars, like we did with the the finger example. You can measure things that are pretty close to your face, but that technique kind of falls apart if I want to know how far away those mountains are. So we need to rely on different techniques at different scales, sometimes called the distance ladder in astronomy. So they're like the smallest scale is the solar system. And so in the solar system, historically, people use like timing of eclipses and geometry to infer how far away the moon is and how far away the sun is. But nowadays, because we have big radar dishes and stuff, we're able to bounce light off of the surface of the moon and off of the surface of Venus to accurately measure how far away the planets are. And then that allows us to figure out, in terms of parallaxes, how far something is on the scale of meters. And then we can use the parallax scale to understand other techniques, which allows us to measure further, which allows us to calibrate other techniques, which allows us to measure further. And this is kind of how distances in astronomy work. It's pretty interesting that at every scale you have a different technique that you use to measure distances, but parallax is one of the classic ones.
Kevin, that's very interesting, because the telescope we are using tonight, the Shane telescope, was used to measure the distance to the moon. In fact, in 1969, when Apollo landed on the moon, Apollo 11 landed on the moon, they put a mirror on the moon's surface and they shot a laser out of using this telescope that we're using, the Shane telescope. And it was a pulsed laser. And by looking at the timing difference between the pulses that were going out and the pulses that were coming back, they measured the distance to the moon. So this kind of bouncing of light of a pulsed laser and measuring the time delay between the departure and the return is exactly how they did it. There's Neil Armstrong would give talks. When he talked about it, he mentioned Lick Observatory because that was what was used. And there are all kinds of funny stories about not having the exact latitude of the observatory and all of those things. Armstrong tells the story that we had to go all the way to the moon to figure out the exact latitude and longitude of Lick Observatory.
That's funny.
So the room that was used to fire the laser from is still there in the basement of this telescope.
Matter of fact, there's a swimming pool under the telescope that contained the cooling system for that laser. And that is still there too.
Cool.
In fact, it's just sitting a few stories below where Dan is sitting.
One other thing besides parallax that you might want to put in the chat, Raja, is the standard candle.
Standard candles, right. If you have this, I'm going to put this in the chat. This is something that people use. to measure distances. You'd like to visit the forbidden pool, yes. The ghost of James Lick swims there.
And he's the only one because it's full of ghost water. You can't actually swim in it.
There's no water there anymore?
No, the humidity would damage the mirror.
That's a good point, okay.
But yeah, a standard candle is another one of these techniques. It's the next rung up in the distance ladder. So on the smallest scales, we bounce light off of things in the solar system to understand how far an astronomical unit is in terms of meters, how far the distance to the sun is in terms of meters. And then we use parallax to measure how far away nearby stars are. And then on the next scale, you have to rely on so-called standard candles, which are techniques to look at different objects in the sky that are at known intrinsic brightness. And what this means is you can imagine having a candle that you know how bright it is. And if I hold the candle near your face, it appears really bright. But then if I walk a football field away and stand at the end, you can measure how bright it appears to you. And based on you knowing how bright it should be, you are able to measure how far away it is. And so that's what a standard candle is. And so in astronomy, a standard candle is something like a type 1a supernova, which when they explode as a supernova, they tend to emit the same amount of light, no matter what. And so if you observe one of these things, you know how bright it should be, and you know how bright you measured it to be. And so you're able to measure how far away that is. And so this is a good way to measure how far away other galaxies are. There's also, and of interest to this project, is classes of stars that change their brightness in very predictable ways. So if you measure the amount of time that these stars fluctuate over, their variability, their period, if you measure their period, that scales with how bright they are. And so if you're able to measure how long it takes one of these stars to pulsate, you're able to infer how bright it should be. And then that, by knowing how bright it should be versus how bright you see it, again, you're able to measure the distance to that star and the stars around it. So, taking all of these together is how we're able to understand distances to stars within our galaxy, stars outside of our galaxy, other galaxies, very distant structures. Yeah, this is a fantastic question.
And in the beginning of this session, somebody asked about the acceleration of the universe. And that's, I think, the furthest rung in measuring how far away something is how fast is it going away from us?
Yeah.
Mm-hmm.
And that is calibrated by standard candle, which is calibrated by parallax, which is calibrated by laser.
Right. These have been fantastic questions.
Hello, my name is Takuzwa Chipunza. I want to ask, how are stars formed?
So out in the the vacuum of space, you might have, early on in the universe, you just have a gas cloud of almost exclusively hydrogen, with some helium also produced in the Big Bang. And this gas cloud, because everything out in space and just like everywhere else feels gravity to everything else, some parts will be closer together just by random chance. And so eventually they'll start moving together because they're gravitationally attracted together. And over time, more and more of this gas will start collapsing in on itself. As this gas collapses in on itself, it starts to heat up, just like, as things fall through the Earth's atmosphere, they heat up because of friction, because they're sliding past each other. Or, as gas moves faster, it becomes hotter. And so as these gas clouds are collapsing in on itself, they start to get hotter, which produces an outward pressure. And so as the star is collapsing inward, there's this building outward pressure. And eventually, those perfectly counteract each other. They create an equilibrium. And so you have the gravitational collapse falling in and the pressure from the star pushing outwards. Eventually it gets hot enough in this gas cloud that's collapsing that elements can start fusing together. And in that fusion of hydrogens and hydrogens forming together to make a helium, you are releasing energy, and that's where this outward pressure is coming from. And so you basically, a star is formed as this gas cloud collapses, and then eventually it gets hot enough and the conditions are right that you can start fusing elements together. And that's the definition of a star. That's kind of early on in the universe, but later on you can imagine any gas cloud will kind of undergo this process where just by random chance there'll be gravitational perturbations that will cause some regions to start collapsing in on itself. And if they have enough mass, they will form a star.
Yeah, today there's like metals that help with that, but it's still kind of not super well understood how the earliest stars formed, because without metals, kind of like the swirling mechanics that we understand today, and like how the stars that form today wouldn't really interact that exact same way. And yeah, it's also thought that like stellar deaths and merging events, like we saw that blasted a bunch of material out, that causes like turbulence, and it perturbs the gas clouds that would just kind of be sitting there, and they also swirl on their own, but it takes like explosions and violent events to kind of mess things up and shake things up and actually encourage movement and encourage these new stars to form. So I think there's actually like pretty good like before and after events of like you can see a supernova go off or something, and then you can see a bunch of stars forming in the gas regions around it not that long after that got incited basically from the nova event going off.
There's a question from Arya. Arya, you're in Hawaii, if I remember correctly. Yeah. What are the differences between the types of quarks that we know about? So quarks are particles that are bigger than electrons, but smaller than protons and neutrons. And it takes 3 quarks to make a neutron, 3 quarks to make a proton. The differences between quarks has to do with how much charge they have, what the sign of the charge is, and how much charge they have. They all have the same mass, but they have different spins and charge, and that's what those are some of the differences between quarks.
Mm-hmm. Yeah, they're kind of like the smaller pieces of the things that make atoms. I grew up learning in my science classes that the smallest pieces were protons, neutrons, and electrons. But turns out protons and neutrons are made up of smaller things, and those smaller things are quarks.
If the charge of a proton is unit 1, electrons have the same charge as protons. Quarks have funky charges. Their units are plus 2/3, minus 2/3, plus 1/3, minus 1/3. So if you take 3 quarks, 2 of them have, let's say, charges of plus 2/3, plus 2/3, and one of them has a charge of minus 1/3. 2/3 plus 2/3 minus 1/3 is equal to plus 1, and that gives you a proton. Whereas if you take quarks where you have plus 2/3 and 2 minus 1/3, that gives you 0, and that gives you, together that gives you a neutron, neutral charge. Thanks, Ricardo. Yeah, so the quarks were, the person who got the Nobel Prize for the discovery of quarks was someone named Murray Gell-Mann, who was a physicist at Caltech, if I remember correctly. So Q-U-A-R-K-S. So it's a great question, Arya. Thank you. Arya is 14 and is asking questions about quarks, which is amazing.
Wow.
Absolutely amazing. Right, Arya, do I remember correctly that you're 14? Yes, 10th grade. That's amazing. That's wonderful.
Yeah, hello, Raja.
Yes,
And
high knowledge.
Yeah, I see it now, 3 minutes past 11. Our school groups, maybe they may want to leave the session. So this has been wonderful. I really enjoyed the questions and the answers. So if we are going to share a recording of this, I think I will have to go again and share with more schools that may not have maybe the internet enough to have live sessions like this. I think we would definitely join the other sessions in November and December. So we will organize more school groups to join these sessions.
That would be
These are
great.
really powerful. So I think maybe if we can have a vote of thanks from maybe Irene Christian College or Banani School, I think that would be great before we leave. Either Banani or Irene Christian College.
Knowledge. Yeah, thank
We're
you.
representing Irene Christian College. Firstly, I'd like to thank the researchers for taking their time to teach us about the various spectrometers in the universe. I'd also like to thank Mr. Knowledge for giving us this opportunity to participate in this event. We really enjoyed, and I can say for the students, they've learned a lot and they're going. So thank you very much.
Thank you. Thank you so much.
Yeah, thanks for just coming. This was great.
Thank you, Raja, and the rest of the team. I think we'll be leaving. We join the
Why is it upside down?
Knowledge, I will send you the recording. I'll also send it to Sam.
I don't think it's upside down.
It looks like someone wants to say something from Banani. Jane. Oh, okay. So I think we'll leave. Bye-bye, everyone.
Bye. Take care. Thank you so much.
Yeah.
Yeah, bye. And thank you for coming.
Stephanie, are you reducing these?
Yeah.
As we go.
Using the transients.
Cool. I was just curious.
No, yeah.
Something happened to us.
I don't know many of you on this call. So Zach, Mexico, Jane is still connected from Banani. Isabella, Herbert, Christopher, if you want to, and Arya, if you want to just type into the chat a little bit about yourself, we would love that. But you're also welcome to ask questions. And I hope this has been something, hope it's been educational. Arya's been on our calls before from Ohana Kilohoku. Arya's been on our calls before. I think when we did this on the 2nd of September, we had an ESI run with Yuting and Eric. Arya was on that call, I remember. We really have connections from all over the world. Zach is a professional neuroscientist in Australia. Zach, thank you for connecting. This is you really are a long way around the world. Isabella, I've heard of KCC, and I'm really glad you've connected from there.
I think we're getting a wave goodbye from Jane. Or maybe that's what that is, or a hand raise. It's hard to say.
That is a hand raised, yeah.
Yeah.
Arya, you can start doing research in astronomy even before you get out of high school. And if you're considering a career after high school, if you're considering a career in astronomy after high school, all the more reason to do something while you're in high school.
Yeah, I'm envious of everyone who gets to take the opportunities that are, well, that I didn't even know existed when I was in high school.
Yeah, these opportunities certainly did not exist for me. Not only I didn't know about them because they didn't exist. They literally did not exist in my time, in my where I was, and there was no such thing as connecting remotely back then. So that was
Why
not an
didn't you?
option.
Yeah, just use the internet, Rasha.
I know the internet had not yet been invented.
It should also be noted that you don't have to be a professional to contribute to astronomy. Many comets and asteroids have been discovered by amateurs.
Good point.
The famous 1987 supernova is also a amateur discovery.
Kevin, are you in Santa Cruz?
Yep.
Actually going to be on campus tomorrow. I realize I have to be on campus.
Yikes.
I've gotten so
I hope
unused
you're
to
not
it.
staying up all night.
Well, I don't have, I'm going to try and attend Kat Daniels' talk in person, the
Yeah.
colloquium. That's at 10:40.
Yeah, I enjoyed her talk on Monday, but I don't think I'm going to be making it to colloquium tomorrow morning.
I may not make it either, but let's see. But I'm supposed to have dinner with her tomorrow and have a like just a usual chat, regular, half-hour chat with the speaker.
Mm-hmm.
No. Kevin, thanks for the terrific explanations, all of you. Raphael, you chimed in. Stephanie, Dan.
It's fun. I always like the. I feel like this revitalizes me and makes me remember why I love astronomy.
Same here. Same here.
Yeah. That's a great question, Zach. I think with a lot of telescopes that were once, the state of the art and the most competitive telescopes in the world that have kind of taken a bit of a backseat to the bigger and bigger telescopes, they're still invaluable for educating young scientists, myself included. This is the first telescope I learned to observe on. And they're a kind of a lower barrier to entry for people applying for time on telescopes, as opposed to some of the much harder to get time on bigger telescopes like Keck, for example. So I still see a very, very valuable place for 1 and 2 and 3 meter class telescopes in the future. And other than that, it's great for types of projects like the one we're on, where you don't necessarily need the biggest telescope in the world to study the targets we're interested in. And because something like we don't need to fight for as much time, and so we can have more freedom to do the things we want on a telescope like this one. That's some of the benefits that I see, and so I see it persisting in the future for those reasons.
Should also be noted that less than 300 meters from where I'm sitting is the Kate telescope. It's an automated robotic telescope. It's about 0.6 meter in diameter. And for most of a decade, it was the most prolific discoverer of new supernova on the planet. So you can do useful science with a small telescope, even now.
Mm-hmm.
Often the smaller the telescope, the bigger the patch of sky it can see at once. Those two things are inversely correlated. The bigger the telescope, the narrower its field of view. So the other thing, exactly as you said, Kevin, is we get so much time on this telescope. It would be hard to get this much time on bigger telescopes. So what matters in the end is not just the rate at which you collect photons, but also the total number of photons you collect. So with these smaller telescopes, where you can get lots of time on the telescope for a project, you can do things that are competitive with bigger telescopes.
And you can do more experimental things, I think, is the other side of it. Like I not to say that the bigger telescopes only ever do safe bets and hedge their bets. But you know, you can do a lot of proof of concept stuff on smaller telescopes, and take if you find something particularly interesting, or you know, justify it, you can bring that to the larger telescopes if you need to, or just continue doing it on the smaller ones. So for example, you know, for some of these really faint targets that we've been going after, if we find something particularly interesting, we might turn around and go to one of the bigger telescopes and see if they are interested in doing follow-up, because they're able to see fainter.
I think also it should be noted that quite a lot of the instrumentation is developed on small telescopes for many of the reasons that Raja and Kevin have outlined. So spectrography was proven on a small telescope before I ever moved to a large telescope.
Adaptive
CCDs
optics.
Yeah, adaptive optics, CCDs, you know, the fiber optic spectrographs were all proven on small telescopes before anybody let them anywhere near the big telescopes.
Yeah. Starlink satellites.
Yeah, but I'm watching.
Yeah, not for our data. We have such a small patch of the sky that we're looking at, so we'd have to get supremely unlucky to have one of them cross our little slit. But I definitely have you know, colleagues and who have been spoiled by Starlink. Yeah, you'll see them at conferences and talks where people will show an exposure that they were doing for a very long time. And if you're looking at a big patch of the sky for a very long time to get these deep images of you know, galaxies and stuff like that, yeah, that's when you're going to run into problems.
Just to put things in perspective, it's not unusual, you know, at least a couple of times per run, we will see something blit through the field of view of this telescope. But if you compare the size of the slit and versus the total field of view of the telescope, even if you have a satellite go through part of the image, it's unlikely that it'd actually go across the slit. And we do, you know, I estimate once a night get a satellite that goes through the field of view, but it doesn't really spoil the science because it doesn't go across the actual sensitive area of the instrument.
So yeah, basically it hasn't been a problem for us on this telescope, but it is a problem for the astronomy community.
I think actually the people that are really suffering from Starlink are the radio guys.
Yeah.
Is that all the communication that is affecting radio?
The thing with Starlink is it's ubiquitous. So, you know, as long as you don't look at something that's near geosynchronous, you were okay up until a few years ago when everybody started putting up CubeSats and then Starlink and whatever the Amazon competition to Starlink is. Now you're always going to have something that's making electronic noise go through your field of view.
Got it.
And even if it's not going through the field of view, the amount of crap we're putting up in the air, you get a lot of reflection. You know, it's like trying to take a photograph when somebody's throwing glitter in the air.
Wow, this is one of the best nights we've had in a long while. I feel comfortable saying that at this point. I wouldn't jinx it if it was midnight still.
Yesterday when I called in, I spoke to Sean briefly, but the telescope was shut down due to high winds, I think.
Yeah,
at the
he was
beginning
saying
of
it
the
was
night.
like 72 miles per hour was like the highest gust. And he was saying the walk home was treacherous. Do you have that too?
So he walked home when the highest gust was 68. By the time he got home, it was 72. And by the time I went home, it was 76.
Oof.
So
Wow.
yeah, it was gusty all night.
So you didn't open it all last night?
No, we did no science last night.
Wow, we're lucky.
Our
Wow.
observer gave up basically at 1:30 because one, he's been doing this a long time and he knows how to read the weather even better than we do. And two, most of his targets were early in the night.
This was Carl Mellis, right? He was. I was
Yeah.
trying to reach him,
I
but
have sent new coordinates to POCO and we are ready to move.
I was wondering when you were going to say that.
Yeah, it's always the second people are starting to
Easing
talk again.
in. Yeah.
I wait for it.
Ambushing people, huh?
Yeah.
It's not
So this is a, where'd it go? 18.3 magnitude star. Should have a nearby less bright blue star. So we'll just be aware of that.
dimmer blue star. Do I have a PA?
Right. PA of 8.9.
8.9. That's not what I wanted to do. This is what I wanted to do. Felt kind of bad that the people with Jane didn't seem to, they got distracted somehow and didn't get a chance to ask any questions.
Yeah, that was unfortunate. I wonder if there's a way we could follow up and get like a email list or something of a few questions. And
so if anybody was watching the guided copy, we just saw a satellite go through our view.
oh, I wasn't
really?
paying attention.
I wasn't.
And the school that Jane's school is in near Lusaka in Zambia, and this is the first time we've had schools, that school or any school from Zambia take part in this thing. I think we've had students from Zambia in our Python tutorial. We've had students from 11 different African countries in our Python tutorial. Well, in one session alone, there were signups from 11 different countries, but by now we're probably 15 or 20 countries. But never in the telescope sessions have we had a school from. I bet Knowledge knows them. And I like your idea.
That Knowledge was coming in from what looked like his car.
He was in his car, right? A big issue that we faced with students in Zimbabwe is, finding good internet bandwidth. So yeah, so to give credit where credit is due, the person who connected, who connected Knowledge and me was a high school student in Palo Alto, in a public school in Palo Alto High School. There's a young woman named.
Right. Are we on?
So I have your blue object. Well, I can't tell it's blue, but it's dim.
Yeah. That's the right spot.
Yeah, it may fall into the slit.
That should be okay.
Okay.
Actually, you know what? Let's just be safe, and rotate away a little bit.
Okay, it's going to take about 15 degrees. Is that all right?
Yeah, that's probably fine. They're so close. I'd worry that it'd be hard to separate them.
So there's 15 there.
Perfect.
Get this other thing decentered.
And there's another question for you in chat, Dan, about how many nights are lost each year at Lick?
Depends on how you define lost. I'm up all night, regardless of whether we're actually doing any science. But we lose usually close to a month in February due to bad weather. And then typically we lose a couple of weeks due to smoke and ash in the fire season. And then we might lose a half night beyond that due to technical trouble. You may set your slit. I don't know if that's the kind of answer they were looking for, but you know, without actually going back through the records, that's approximately the magnitude of it. And you may begin.
Perfect, thanks. We'll be here for 40 minutes. There was another question about seismic activity for if that's a concern for the telescopes. And I think the answer is no, because of the way they're constructed, where you sink a really deep concrete pillar into the ground first, and the telescope is like disconnected from the building so that it's kind of insulated from those things. But Dan, maybe you have more insight into that.
So the really big concrete pillar theory works well for a small telescope on a new mount.
Okay.
This is not a small telescope and it's not a new mount. The APF, which is 100 meters or so to the west of me, does have an isolated mount. And so the kind of everyday seismicity, you know, the little micro earthquakes that you can't actually feel, don't affect it much. They don't really affect us here much because the telescope is massive and the amount of earth movement we get is very small, and the automated guider can correct for it. Larger earthquakes, however, are an issue. Particularly if the telescope is moving at the time, it can damage the drive gears. And we've got a bunch of shock absorbers and weird springs and things like that to mitigate that. But on a decadal scale, we are on the plate boundary between the Pacific plate and the North American plate. And the ground under us does in fact move. And therefore we have a certain amount of adjustment built into the mounting of the telescope relative to the building. Matter of fact, one of my duties is about once a week I go down in the basement and check that the adjustments are where they're supposed to be. We haven't had a little earthquake that's bounced them around. And if they're not, there's a little hydraulic jack, a little hand jack, and I operate a couple of valves and I can actually move the telescope by hand back to where it needs to be. If we were to have a large 1906 class of earthquake, it would probably exceed the adjustments that you can make with that jack, and we would have to actually shim the telescope relative to its mounts to the building so that we would have enough room to adjust in the future. Thus far, that hasn't happened, but there are at least 3 active faults that are within a 15-kilometer radius of where I'm sitting. Funny historical aside, in 1906, Lick Observatory had a meridian circle, which is a way of looking up at the sky and determining when something is directly overhead. And they would make a noon sunshot and send out via telegraph, the exact time that the sun went overhead to pretty much the entire West Coast. So we had a telegraph up here and a telephone up here pretty early in those technologies. And so in 1906, somebody noticed after a couple hours that, hey, you know, there's nothing coming in on this telegraph. We should probably check on that. So somebody looks out to the north and sees this gigantic column of smoke. And they're going, okay, that's weird. And so they grab one of the telescopes that's mounted on a big pile of bricks over in the main building, and they swung it down and pointed at San Francisco and watched San Francisco burn after the 1906 earthquake.
Wow.
Wow. This telescope was, yeah, that was using the great refractor.
No, that one won't depress far enough. It was the 12-inch Clark that was on the other end of the building where the nickel is now.
I see. This is from Alvin Clark and Sons.
Yeah, I believe that telescope is down at campus at this point. I know it still exists. I just don't know where it is. So, anyway, I bring up that little historical anecdote to say that, yes, there is a seismic connection, but it's not what you might expect. Since we're sitting on this nice bright object, so seeing is now somewhere between 1.2 and 1.4 arc seconds.
Okay.
Wow.
That's
That is really good. Hi, Alicia. Alicia, how did you find out about our observing? Was it through Ohana Kilohoku?
Okay, we're reading out on red. I'm sending new coordinates to POCO, and we are ready to move.
And we're on the way.
Okay.
Noticed it got awfully quiet all of a sudden.
Yep. It's great.
That's
I'm making a lot of headway on my moving now. I have a PA of 154.
One, 5, 4.
This is gonna be a faint one. And
Have any that are bright?
I mean, bright for us is like 16th magnitude. Yeah, like 18.9, I think, for this one. And it's not the center of the galaxy that we're going to. So that's why I sent you offsets.
Okay, I'll look those up in just a second. If I don't close the bloody thing first, why do we even have that stupid button? Not the center of the galaxy.
Oh, it's doing the same server failure thing. So hopefully it goes through now.
Of course it is. Microsoft is involved, and one of the first technologies they perfected was the critical need sensor.
They've integrated that into every printer I've ever used.
Every operating system they've ever published too.
Technology smells fear.
That's 21.
I'm rapidly turning into a pumpkin, so I think I'm gonna call it a night.
How seasonal of you.
Very seasonal. Yes. I'll turn into a turkey too.
I'm not even going to touch that one.
What am I going to turn into later in the holidays? Douglas fir.
You're evergreen, Russia.
Thank you. I'm full of needles.
Like I said, I'm just not going to touch that one. All right. We are very much not in the right place.
Did I not enter the coordinates correctly?
No.
Because I've done that before.
Big slews confuse the pointing model. Okay, so we are in this configuration. More or less. So this is gold, that's blue. We'll use gold.
Kind of fun that it's in the middle of like a triangle of stars.
Okay, and then front goal, we're going 18.66. West, 2.38. You may set your sled. And you may begin. You guys probably get tired of listening to me click this mouse.
It's no, it's not maybe as loud as it is on your end. So
Well, it's right next to the speaker, so I'm sort of shocked that it's not blowing somebody's eardrums out.
maybe there's some smart determining of what sounds to mask.
Maybe. At any rate,
Yeah,
yeah,
we're gonna be here for a while.
I'm gonna go have a look at the sky and have a little walk around and stretch my legs, and I'll be back.
Sounds good.
Hey, Sam. Hey, Sam.
Sorry, I had my sound off. How's it going?
It's good. Wow, it's late at night for you.
Yeah, I
Past
got
midnight.
stuck. I got stuck watching the Squid Games.
No spoilers. I've only watched the first 3 episodes.
Oh man, I just beat you to number 4.
Okay.
We had
It's,
a wonderful turnout, Sam. Wonderful. There were people from Australia who found out about us through Anakila Hoku, who had connected a couple of people from Australia.
No way.
No, we had someone connect who works at IRTF, but used to work at Lick, so knew a lot about the Shane telescope, etc.
That's awesome.
And then from midnight to 2, we had a group, midnight to 2 our time, so 9 to 9 to 11 your time, 9 p.m. to 11 p.m. your time. We had a group connect, two groups, one connect from Zambia, one connect from Zimbabwe, two school groups. So it's been quite a night of outreach. And it's been a spectacular night from observing conditions-wise, very good conditions here.
That's great. That's great. You guys are still recording too, so people might actually get all the way to the end here with you guys.
I probably should stop recording though, because we haven't been answering questions in a little while. Zach,
How
in fact,
long?
yeah, sorry, go ahead.
How long were people on?
Oh, pretty much the entire time. They connected at 7:30, a few minutes before I joined. And it was only until just a few minutes ago that we had, discussions on the chat, questions.
Oh,
so
wow.
long time.
Oh, wow.
It, it ebbed and flowed. There were times when there were lots of questions. When the students from Africa were connected, there was a regular stream of questions. But there were also periods when Kevin and others were explaining what we were doing. And so there's lots of good material, I think, for other students to see what goes on in these sessions.
I thank you guys for letting us come on here. It's been a real pleasure. It's so cool that you guys let us come here and watch this stuff. So yeah, I have no idea who will make it to the end of this video if we ever put it on the internet.
Yeah.
But if you guys got any more stuff going on until 3:15, I'm happy to post it. That's the plan anyway, and see what kind of response it gets. I'm sure. I have anybody ever posted anything like this before, like an actual observing? I would think someone had, but maybe not. Maybe it just hasn't happened.
I don't think so. I don't think so. I don't think anyone's posted a whole night of observing, or this is what is close to a whole night. I was actually going to hang up soon, Sam, because I have to get up and drive to Santa Cruz in the morning. But I think it's certainly portions of this were intense with great questions, and the chat will also be part of it. You'll see there's a lot in the chat. There were great questions from Arya was on the call.
Yep.
This was like our third time connecting.
That's awesome.
Yeah.
That's great. What are you guys finishing up with now? What's the last 3 hours going to be?
More of the some transients at the end, but a lot of variable stars we've been doing so far, right, Kevin?
Yeah, we kind of jump all over the place, mostly focusing on variables in Andromeda, but based on when things are up, we bounce over to some nearby transients as well. And now we have a few high priority transient targets for the last few hours of the night.
Transients
so
that's
what we're
people
doing.
passing in front of stars.
No, those are transits.
Oh, transits.
So transients are things that come and go. They show up, and then they disappear. There are even classes of things called recurring transits, where the same object shows up, disappears, shows up, disappears. So these are extreme variations in brightness, is what they are. And whereas something like a variable object, they're continuously visible, but just their brightness changes with time.
So yeah, the classic transients people think of are things like supernovae. They blow up, and they were a normal star and you could barely see them, or not at all, and then suddenly they're brighter than a galaxy for the course of a month, and then they're gone for forever. So those are the kinds of things we're ending the night on.
Yeah, that's what I figured. It's a supernova. That's so something actually. So this actually happened, didn't it? I don't know if it was a transient, but it was just like, well, we had like two black holes crashing into each other or something, and like I saw this in the news, right? Like every telescope on Earth looked at it one night.
That's
yeah.
right.
Yeah, that would have been the back in 2017. That would have that was led by a group at Santa Cruz, actually. It was one of these cases where LIGO measured gravitational waves from I guess it was two neutron stars merging together.
And then 2 years before that, there were the first detection of two black holes, and then there were
right. Yeah, so two neutron stars merging together, and there was a confluence of events where, coincidentally, a few other things were able to kind of localize where on the sky people should be searching. But yeah, it was like everyone who had access to a telescope was frantically searching. But the Santa Cruz team was the first group to identify where, the host galaxy, where this thing was in, figure out this. So yeah, the first group to get a electromagnetic counterpart to a gravitational wave source. And for the next month or so, yeah, it was like the most studied object. Like it was constantly being watched by all the telescopes that were possible. And I think for a while it was like the most studied, the most observed object, full stop, aside from the sun or something.
That is totally awesome. So, okay, well, have fun. My 3-year-old decided that he was going to come out and watch the observation today. Have a good day. So I'm going to have to go and have fun now.
All right, Sam, you take care. We'll be in touch. You and I will be in touch soon.
Okay,
I'll
that's
send you the
awesome. Thank you, guys. Aloha.
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 Kevin, Dan, Stephanie, Raphael, Zach, I'm going to hang up.
Good night, Roger.
Good night. I'm going to stop recording. Thank you guys for
Get some
being
rest.
such amazing amazing educators today, and in addition to being amazing researchers. So
Like I said, it was great to do, and yeah, always reminds me of why we do what we do.
yeah, and
We're ambassadors to the stars.
we are, and as you said earlier, Kevin, it really resonates with me, the idea that every time we do this, we learn something. Every time we have to explain something in a different way. I find I learn something when I have to explain something. Yeah, it was a lot of fun.
Yeah. Thanks.
Okay, you guys take care.
Okay.
You will see this recording at some. When I send out the recording, I'll send it to you. Send it to all of you. And Zach, let me know, please, if you're interested in seeing the recording, or you can, Sam will post it anyway, so you'll see it through that. Okay, take care.
Take care, Raja.
Bye.
You too.
Good luck. Dan, thanks.
All right, Rajan.
Night.
Next time. See you
Till
tomorrow.
tomorrow night. Yeah, see you
Yeah.
tomorrow.
Gonna do the education thing again?
There will be one group from Africa connecting at midnight. This much I know. I think there might be Ohana Kilohoku attendees tomorrow as well.
Okay, so
Okay,
we're gonna connect your
let's
Zoom again?
use the Zoom link. What I've done is I've called it Lake Observatory Shadow the Scientist, which is what we've been calling this program. And what I can very easily do is keep changing the password each time. But I think for tomorrow night, let's just use the same link.
Yeah, I think the concern here was that we don't like to change the password on our Zoom much.
Exactly.
And so we didn't want a bunch of gate crashers who got the date wrong or something.
That's right. That's right.
Next
So
month.
I
So-
think this is a good solution. Paul came up with this notion that I wasn't sure whether, whether this would, how it would work out, but this has worked out beautifully. I think just having the, we're all connecting to a call that's set up through my account, and for now I'll just hang on to this, and if it gets too widespread and we find we're getting gate crashes, it's trivial for me to change the password.
Right. So, at any rate, all's well ends well, and we'll see you tomorrow.
Take care. Bye.
Bye.